66 million years ago, a world of thunder and giants ended in a single breath of geologic time. But was it fate, or a perfect storm of catastrophes that could just as easily echo in our own future? The last morning of the Cretaceous looked like any other. Sunlight filtered through canopies of magnolias, ferns, and towering conifers, painting the swamps and rivers of North America in golden hues. Herds of triceratops grazed across the floodplains, their horns glinting as they browsed. Tyrannosaurs prowled at the edges of forests, eyes fixed on prey. Farther inland, ankylosaurs, armoured like living tanks, smashed through thickets in search of ferns. High above, pterosaurs with wingspans longer than a bus soared in the rising air currents. Out at sea, giant mosasaurs and plesiosaurs hunted beneath rolling waves, while spiralling ammonites drifted like ancient jewels through the deep. Life thrived, bold and diverse, as if nothing could ever dethrone the dinosaurs from their throne as rulers of Earth. But the stability of a world is always an illusion. While the dinosaurs went about their final day, a rock the size of a mountain hurtled through space at more than 20 kilometers per second. It had wandered for millions of years in the asteroid belt, invisible to the creatures below, until fate nudged it onto a collision course. When it struck, its energy would equal billions of nuclear bombs exploding at once. That singular instant 65 million years ago has long been remembered as the apocalypse that ended the age of dinosaurs. But the deeper one peers into Earth's rocks. The less simple the story becomes. We love clean answers. An asteroid killed the dinosaurs is easy to memorize, dramatic to tell, and clear enough to put in a classroom diagram. Yet the fossil record is rarely simple, and the truth of extinction is never neat. Alongside the famous impact crater in the Yucatan, we find evidence of volcanism on a scale beyond anything humans can imagine. In what is now India, the Deccan Traps were erupting in titanic fits for hundreds of thousands of years before the asteroid appeared. Lava poured across the land in floods of fire, sometimes over 500,000 cubic kilometers, enough to bury entire countries. Each eruption belched out choking sulfur and carbon dioxide, altering climate systems and filling skies with haze. The greenhouse world of the late Cretaceous began to flicker between extremes: searing heat, chilling cold, storms, and acid rains. Forests died back, oceans grew more acidic, and reefs collapsed. Long before the impact, ecosystems were already under enormous strain. Even the dinosaurs were showing cracks in their dominion. Some lineages were diversifying less, their populations thinning. The hadrosaurs, once abundant across continents, saw declining numbers in some regions. Predators that relied on stable prey herds began to falter. Food chains, always fragile, stretched thin. At the same time, sea levels were falling, exposing continental shelves and shrinking the warm, shallow seas that had supported so much life. The world was shifting beneath the dinosaurs' feet, geologically and climatically, and though they still dominated the land, their hold was less secure than it appeared. And then the sky fell. The asteroid slammed into the Yucatan Peninsula with a force beyond comprehension. In seconds, ocean water vaporized, stone turned to plasma, and a crater more than 150 kilometers wide tore open the Earth's crust. Shockwaves radiated like the heartbeat of a dying world, toppling forests thousands of kilometers away. Ejecta melted rock and ash shot into space and rained back down as fireballs, igniting global wildfires. Tsunamis, hundreds of meters high, ripped across coastlines, scouring everything in their path. The immediate devastation was apocalyptic, but worse was still to come. As fine dust, soot, and vaporized sulfur circled the globe, sunlight dimmed, photosynthesis faltered, temperatures plummeted, first from the shroud of dust that blocked sunlight, then from chemical reactions in the atmosphere that depleted ozone and triggered acid rains. A nuclear winter swept the globe, darkening skies for months, perhaps years. Plants died, herbivores starved, predators followed. Only the smallest, most adaptable creatures, those that could eat seeds, burrow, scavenge, or endure in water, had much chance of surviving. The asteroid was not the sole villain of this story, but the final blow in a chain of catastrophes. Without the long volcanic winters of the Deccan Traps, perhaps ecosystems might have absorbed the shock. Without the falling seas and disrupted climates, perhaps food chains would have rebounded. But fate aligned multiple disasters in a single geological moment, turning crisis into annihilation. The dinosaurs did not simply vanish in a day. They were cornered by a convergence of disasters, and the asteroid was the executioner. This is the real shock hidden in the rocks. Extinction is rarely the work of one hand. It is the result of stress piled upon stress, disaster upon disaster, until even the most magnificent creatures collapse. The dinosaurs, giants of strength, power, and resilience, were not simply outmuscled. They were undone by timing, by misfortune, by the convergence of earthbound catastrophes with a visitor from the heavens. Imagine, then, the bewilderment of that final generation. The ground trembling from eruptions, skies stained red with volcanic haze, seas creeping back from their shores. And then, without warning, a light brighter than the sun, a shockwave hotter than fire, and a world plunged into eternal night. Herds of triceratops wandering into dead forests, tyrannosaurs hunting among carcasses, only to starve themselves, pterosaurs, once kings of the sky, dropping lifeless as the air turned cold and empty. It was not only death, but disorientation, the sudden realization that nothing would ever be the same. Yet, life endured. Not all dinosaurs perished. A lineage of small, feathered species, those nimble enough to feed on seeds and insects, slipped through the bottleneck. We know them today as birds. Crocodiles survived in rivers and wetlands. Mammals, small and adaptable, thrived in burrows and niches where giants could no longer dominate. Extinction cleared the stage, but evolution kept writing the play. So, what really killed the dinosaurs? Was it an asteroid? Yes. Was it volcanism, climate collapse, falling seas, fragile ecosystems? Yes, it was all of these, converging in one of the rarest alignments in Earth's long history. Dinosaurs were unlucky not because they were weak, but because catastrophe came from every direction at once. This story shocks because it reveals a world undone not by a single villain, but by a perfect storm. It reminds us that strength is no guarantee of survival, and that domination of the planet can vanish in a moment. It is a lesson written in ash and stone, in craters and lava fields, in fossils of creatures that once seemed eternal. The end of the dinosaurs was not the end of life, but it was a warning about the fragility of all life, including our own. For millions of years, dinosaurs had reigned supreme, their footsteps shaking the earth. But on that one final day, their world ended. Not because they failed, but because disaster struck at the very moment they could least endure it. And in that ending, the seeds of our own beginning were sown. They come in all shapes and specialties, scattered across universities, museums, and field camps. But they share one obsession: piecing together the greatest murder mystery in Earth's history. To the outside world, paleontology might look like the study of dusty bones, but the women and men who dedicate their lives to it see themselves as detectives, trained to extract stories from fragments of stone. A femur is not just a fossil, it is testimony. A thin smear of iridium in a cliff face is not just a chemical anomaly, It is a crime scene marker. These scientists step into the void left by vanished worlds and ask questions no witness can answer. And yet, through persistence and imagination, they summon a past that ended in fire and silence. The cast of sleuths is diverse. Paleontologists work with brushes and chisels, crouched under the blazing sun in Montana Badlands or on windswept Argentine plateaus, carefully freeing fossils from the rock that entombed them for tens of millions of years. Each fossil becomes a clue, a time-stamped record of life that thrived before the curtain fell. They know where the trail goes cold. A sudden break in the fossil record, an abrupt absence of once plentiful creatures. They are the crime scene investigators of deep time, charting who lived, who died, and who somehow slipped through extinction's fingers. Then there are the geochemists, the ones who trade bones for dust. They sample ancient sediments layer by layer, examining the fingerprints left by planetary catastrophe. In their labs, machines hum and whir, detecting concentrations of elements so small they would pass unnoticed by human senses. To them, the thin clay layer that circles the globe is not just dirt, it is a message, a spike of iridium. Far rarer on Earth's surface than in the hearts of asteroids, appears like a calling card, left behind by something unimaginably violent. These scientists are less bone hunters than forensic chemists, finding poisons and residues that tell of firestorms, acid rains, and global darkness. Planetary scientists enter the scene with an even larger canvas. They study the scars of celestial collisions, the pockmarks of craters that punctuate our planet's surface. From satellites orbiting high above, they trace circular depressions buried under jungles and seas. The faint fingerprints of ancient impacts. It was planetary scientists who looked at the Chicxulub crater in Mexico's Yucatan Peninsula and declared, "Here is the smoking gun." To them, the extinction of the dinosaurs was not just a biological mystery, but an astronomical inevitability, the day the solar system itself reached out and rewrote Earth's history. But if science were that simple, there would be no story to tell. Not all detectives agree on the culprit. Some point to massive volcanic eruptions in India, the Deccan traps, as the real executioners. Basaltic lava that flowed for hundreds of thousands of years, belching carbon dioxide and sulfur into the skies, may have cooked the climate and poisoned the oceans long before any asteroid struck. Geologists map those flows and count the pulses of lava like a cardiogram, arguing that the heart of the Earth itself was the killer. Others weave together both threads. Volcanoes weakening ecosystems, the asteroid delivering the coup de grace. In this version, Earth was already reeling, and the final blow merely finished what tectonics had begun. The story grows more complex as other scientists enter the investigation. Paleobotanists, studying fossilized leaves and pollen, note how forests thinned and changed in the run-up to the extinction, suggesting ecosystems already under stress. Paleoclimatologists analyze isotopes locked in ancient shells and conclude that temperatures swung wildly in the late Cretaceous, plunging some regions into seasonal extremes. Marine geologists dredge the ocean floor and find signs of acidification, the water chemistry shifting in ways hostile to life. It begins to look less like a single gunshot and more like a conspiracy of assassins, each environmental stress compounding, until life's resilience finally broke. Each of these detectives is driven by more than academic curiosity. There is the urgency of knowing that Earth has been struck before and will be struck again. For planetary scientists, understanding Chicxulub is not just history, it is survival. They calculate orbits of near-Earth objects, track asteroids with cold precision, and remind us that dinosaurs did not have telescopes or rockets. Paleontologists, too, feel that urgency. To understand how ecosystems collapse under sudden catastrophe is to glimpse our own vulnerabilities in the age of climate change. Geochemists warn that the same gases belched from Deccan volcanoes are now pouring from our smokestacks. The story of dinosaur extinction becomes less ancient tragedy than cautionary tale. And so, this ensemble cast takes shape. The fossil hunters with sunburnt necks and calloused hands, crouched over bones that once carried giants. The geochemists with their mass spectrometers, chasing ghostly signatures of catastrophe. The planetary scientists mapping the craters of doom from space. The botanists, climatologists, and oceanographers, each offering a thread that must be woven into the tapestry of extinction. They are united by the conviction that the past speaks, if one listens closely enough. Each discipline brings a different dialect, but together they tell a single story, how a world of thunder lizards vanished, and how their disappearance remade the stage for everything that followed, including us. They argue, they publish, they challenge one another's data. Rivalries flare, as with any great detective tale. But the friction sharpens the picture. Slowly, over decades, the outlines of the catastrophe have emerged, not from a single revelation, but from countless hands assembling puzzle pieces scattered across continents. The bones in Patagonia, the iridium in Italy, the crater in Mexico, the lava flows in India, all are stitched into one forensic narrative. The detectives of deep time do not work in isolation, but in a global collaboration that spans languages, borders, and specialties. As the camera of imagination lingers on their work, one sees the drama not only in the vanished dinosaurs, but in the living scientists who chase their ghosts. They kneel in the dirt, grind samples in sterile labs, or run simulations on glowing computer screens. They are heirs to Sherlock Holmes and Agatha Christie. But their mystery is real, and its consequences echo in the air we breathe and the skies we watch. The extinction of the dinosaurs is not just a tale of the past. It is a mirror held up by these detectives, in which we glimpse both our fragility and our astonishing capacity to understand. Bones are silent things when you first see them, half buried in sandstone or clay, bleached by the sun, weathered by time. Yet to the trained eye they are not mute at all. They whisper of lives lived and lost, of seasons of plenty followed by sudden scarcity, of herds that thrived and then dwindled. Fossil beds are not just collections of skeletons. They are time capsules that preserve the rise and fall of entire ecosystems. To understand why the dinosaurs vanished, one has to read the subtle shifts in those bones, the quiet warnings etched into the fossil record long before the final day of reckoning. In the late Cretaceous rocks of Montana, for example, paleontologists have mapped layer upon layer of Triceratops remains. For millions of years, these great horned herbivores seemed stable, present in abundance. But as the Cretaceous wore on, their diversity waned. Fewer species appeared in the record. The horns and frills of their skulls, once wildly varied, grew more uniform. It was as if evolution itself was slowing down, the once vibrant experimentation of nature narrowing toward a dead end. Bones that should have testified to flourishing now spoke of stagnation. Other fossil beds tell similar tales. Hadrosaurs, the duck-billed grazers that once ranged from Alaska to Patagonia, show signs of decline in certain regions. Their teeth, perfectly adapted to grinding tough plant matter, became less common in younger layers. The herds that had dominated floodplains were shrinking. Predators followed suit. Tyrannosaurs, magnificent apex hunters, remained, but in fewer numbers. Even they seemed stressed, some skeletons showing malnutrition, injuries that never healed, evidence of animals pushed to their limits in ecosystems no longer capable of supporting them at past levels. The rocks are not dramatic about these revelations. They do not announce catastrophe. They whisper it. A thinning here, a missing species there, a subtle shift in abundance. It is only when the layers are read together, when the story is stretched across hundreds of thousands of years, that the pattern emerges. The dinosaurs were already in trouble before the asteroid ever appeared. Clues lie not only in bones, but in the sediments that entomb them. In New Jersey, Delaware, and across Europe, scientists find shells of marine creatures, ammonites, clams, plankton, vanishing in step with the land animals. Whole food webs in the oceans were faltering. The chemistry of those shells tells why. Increased carbon in the seas, acidification that dissolved calcium, and temperatures that swung violently. These were stresses no creature could easily endure. The whispers in the bones were echoed by murmurs in the shells. Together, painting a portrait of a planet staggering toward crisis. Even plants leave traces of the story. Fossilized leaves carry the scars of insect chewing, evidence of plagues that sometimes flared when ecosystems weakened. In the last million years of the Cretaceous, those scars multiply. Forests struggled. Spores of fungi surge in some deposits, hinting at dying vegetation feeding sudden blooms of decay. What seems a lush world in paintings of the age may, in truth, have been patchy and unstable, with green but fragile ecosystems. For herbivorous dinosaurs, that instability meant hunger. For predators, it meant famine. The bones also tell of boom and bust cycles. Entire beds filled with thousands of animals suggest die-offs from drought or flooding, disasters that swept through populations. Some sites show repeated patterns, mass deaths layered one upon another, each separated by years or centuries of reprieve. These rhythms of crisis left dinosaurs weakened, their populations battered by waves of mortality. When the final catastrophe came, they faced it not as vigorous empires of nature, but as exhausted survivors already on the edge. And yet, fossils whisper of resilience too. Small mammals scurrying in the shadows of giants multiplied during these last ages. Tiny teeth, barely larger than a grain of rice, litter the layers, testimony to rodents and insect eaters adapting to changing environments. Birds, descended from small feathered dinosaurs, spread into new niches, some with beaks perfectly designed for cracking seeds that could survive long winters. The record shows not just failure, but adaptation, as if life itself was hedging its bets against looming catastrophe. The most haunting whispers are those of absence. A species appears in older rock, then simply ceases in the younger. No drama, no explanation, just silence. The vanished are never announced. Their bones stop appearing. For paleontologists, this absence is louder than any presence. It is the gap in the record that speaks most clearly, telling of populations that dwindled until they left no trace. Extinction is not always a sudden event. Sometimes it is a slow unravelling, a gradual fading from the stage. When the asteroid finally struck, it ended what was already unravelling. The fossil beds show this with merciless clarity. Diversity had been narrowing, stress had been mounting, ecosystems were fragile. The impact did not strike a healthy, thriving world at its peak. It struck one already whispering its own warning. The bones tell us that extinction rarely comes from a single blow. More often it comes from many wounds, some small, some vast, until one final strike pushes the world past the point of return. To walk through a fossil bed is to walk through a library of whispers. Each skeleton, each shell, each leaf impression is a fragment of testimony. Together they speak of cycles of prosperity and collapse, of creatures that endured and those that could not. The whispers accumulate until they become a chorus, and the chorus tells us the truth. The age of dinosaurs was not ended by an asteroid alone. It was ended by a planet under siege, by ecosystems stretched to breaking, by a world that had been warning of its fragility long before the sky itself fell. It is only a smear of clay, barely a centimetre thick, but it runs like a scar across the world. You can find it in the Badlands of Montana, in the cliffs of Denmark, in Italian quarries, in layers of rock from New Zealand to Spain. Wherever the sediments of the late Cretaceous meet those of the Paleogene, the same band appears, as if someone pressed a ruler line into the Earth's memory. Above it, mammals and birds and the seeds of a new world. Below it, dinosaurs, ammonites, giant reptiles, an empire in decline, about to vanish. That line is the fingerprint of catastrophe, and for decades it has been at the centre of one of science's most audacious arguments. In 1979, physicist Luis Alvarez and his son Walter, a geologist, were examining this clay layer in Gubbio, Italy. They were struck not by what was present, but by what was absent. The sediment, representing thousands of years, contained no sign of the steady trickle of microscopic fossils, plankton, pollen that should have filled it. Instead, it was barren, as if life itself had blinked out. When they tested it for trace elements, they found something astonishing. An iridium concentration dozens of times higher than normal. Iridium is rare on Earth's surface, but abundant in asteroids. To the Alvarezes, this was the smoking gun. A cosmic body had struck Earth at the end of the Cretaceous, scattering a dusting of space metal across the globe. The claim was electric, outrageous. For over a century, most paleontologists had explained extinctions as slow, gradual affairs species, declining over millions of years, pressured by climate or competition. Catastrophe was considered a relic of superstition, not serious science. Yet here was a bold hypothesis, a single day, a single impact, capable of remaking the world. The thin clay layer, infused with iridium, seemed to prove it. It was the fingerprint of a planetary murder weapon. But fingerprints are tricky things. They identify, but they do not always explain. Iridium showed that something extraordinary had happened, but not what else had conspired to make that moment fatal. Critics pointed out that volcanic eruptions can also release iridium. The Deccan traps, spewing lava across India in the same window of time, could have enriched sediments with similar anomalies. Others argued that extinction patterns looked too stretched out, too drawn over hundreds of thousands of years, to be explained by a single instant. The clay was clear, but the crime scene was complicated. Still, the evidence mounted. Across continents, the same iridium spike appeared with uncanny precision. Fossils above the line belonged to a different world than those below. Ammonites, once abundant in every sea, vanished entirely. Forest ecosystems changed dramatically, their pollen signatures shifting within that narrow band. A fungus spike appeared in some regions, the bloom of decay feeding on global die-off. Everywhere, that line marked not just an end, but a rupture. The case for impact grew stronger. Eventually, the buried Chicxulub crater was found in Mexico's Yucatan Peninsula, precisely the right age and scale to match the Alvarez hypothesis. It gave the fingerprint its hand, the weapon its wound. Suddenly, the iridium line was no longer a mystery. It was a record of the sky itself falling. The impact threw so much debris into the atmosphere that iridium and other metals were scattered across the entire planet, settling in that centimetre of clay. The fingerprint was real, and the suspect had been caught. Yet even this did not close the story, for while the line shows impact, it does not capture the fragility of the world it struck. Dinosaurs had already seen declining diversity in some groups. Oceans were stressed, their chemistry shifting. Volcanoes were still erupting in India, releasing pulses of carbon dioxide and sulfur. The fingerprint identifies the moment, but not the slow weakening that made the victim vulnerable. A healthy ecosystem might have absorbed more shock, rebounded from devastation, but a weakened one crumbled. The clay marks the bullet, but not the sickness, already spreading through the body. The line itself is haunting to see in person. In New Jersey, you can run your finger across it. Below, a world of chalky limestone filled with shells of vanished creatures. Above, a darker layer where survivors struggled into a new age. It is unnerving in its simplicity. A single swipe of clay, and all of prehistory pivots. Dinosaurs below, mammals above, ammonites below, modern seas above. No myth or legend could craft a symbol so stark. The earth, it seems, wrote its own obituary in rock. What the fingerprint in the clay truly revealed was not only the cause of extinction, but a shift in how we understand history itself. For centuries, we imagined the world as steady, shaped by gradual erosion and slow evolution. The iridium line forced us to admit that sometimes the earth changes in a moment, in fire and darkness, in years of ash that feel like eternity. It showed that life is not only fragile, but also at the mercy of chance, of space rocks and volcanic rifts, of coincidences too vast to predict. And that whisper in the clay carries forward to us. For the iridium is still there, a reminder that catastrophe is never entirely past. Near-Earth asteroids are tracked now with obsessive care because we know what their fingerprints can do. Climate scientists study the Deccan traps as analogues for our own carbon emissions, knowing that gases can warm and acidify oceans as effectively as any impact. The clay is not only history, it is a mirror, showing us what fragility looks like written into stone. So the story of extinction is written in a band no thicker than your thumb, a boundary you could step across in a single stride. One side holds a vanished empire of thunder lizards and ammonites, the other, the ancestors of our own world. A fingerprint pressed into clay, circling the globe, tells us that history turned on a single violent instant. But it also warns us never to mistake simplicity for truth. The asteroid left the mark, but the Earth itself supplied the stage. The clay is not just a fingerprint. It is a signature of how chance and vulnerability, space and stone, conspired to end one age and begin another. Beneath the jungles of the Yucatan, hidden under a blanket of limestone and mangroves, lies a scar so vast it can only be seen from the sky or from the instruments that peer into the earth itself. For centuries, no one knew it was there. Locals built villages above it. The Spanish carved out cathedrals, and generations passed, unaware that below their feet lay the wound that had changed the history of life. Only when scientists began tracing gravity anomalies, mapping seismic echoes, and drilling cores did the shape reveal itself. A crater, more than 180 kilometers wide, gouged into the planet in an instant of unimaginable violence. Its name, Chicxulub, comes from a small coastal town nearby. The mark it left, however, is global. The discovery began with hints. In the 1970s, geophysicists surveying the Yucatan Peninsula noticed subtle circular patterns in the data variations in gravity and magnetism that suggested buried structures. Oil companies drilled exploratory wells and pulled up shocked quartz, glassy spherules, and other impact signatures, but the dots weren't yet connected. It wasn't until the iridium line had already electrified scientific debate that eyes turned back to Mexico. If an asteroid had struck at the end of the Cretaceous, where was the crater? In the jungles and beneath the Gulf? The answer waited. Seismic mapping drew the first clear picture. Sound waves shot deep into the crust, bounced back to reveal concentric rings, like ripples frozen in stone. Unlike volcanic calderas or erosional basins, this was something else entirely. The unmistakable geometry of an impact crater. At its center lay a feature even more startling, a raised ring of peaks, not mountains in the ordinary sense, but the rebound of Earth's crust itself, blasted down and then springing back in molten, chaotic waves. This peak ring, encircling the crater's center, marked Chicxulub as one of the largest and most complex impact scars on the planet. Drilling into that buried structure gave the wound texture and depth. Core samples brought to the surface told a story of seconds stretched into stone. Layers of melted rock, microtectites formed from vaporized material that had rained back as glass, shocked quartz grains, fractured at atomic levels, all testified to pressures and temperatures far beyond any volcanic eruption. One drill site even recovered limestone shattered and then cemented by the violence. A record of seabed turned inside out. For geologists, each meter of core was not just data, but a front-row seat to apocalypse. The energy released in that instant defies human imagination. By some estimates, the impact unleashed more than 100 million megatons of TNT, equivalent several billion times the power of the bombs that scarred the 20th century. The asteroid itself may have been only 10 to 12 kilometers across, but at that velocity, it was less a rock than a cosmic bullet, carrying kinetic energy enough to melt the crust, boil the ocean, and send shockwaves rippling around the globe. The peak ring itself, a feature once doubted, proved how violently Earth's crust had rebounded, rising up and collapsing in moments to form the ring of hills still buried beneath Yucatan sediments. Timing, too, emerged from Chicxulub's rocks. Cores taken from deep within the structure preserved microfossils of plankton, their shells cut off precisely at the boundary. The crater wasn't older, as some skeptics once argued. It was exactly the right age, dating to 66 million years ago, within a margin of mere tens of thousands of years. It matched the iridium layer, the fossil record, the collapse of ecosystems. Chicxulub was not just a scar from some distant age. It was the scar, the wound left by the very event that ended the dinosaurs' reign. And yet, what is most haunting is not simply the evidence of destruction, but how the Earth absorbed it. Models suggest that the asteroid struck in shallow water, rich in sulfur-bearing rocks. The location was cruelly efficient. The impact vaporized those rocks, releasing massive amounts of sulfate aerosols into the atmosphere. These particles reflected sunlight, plunging the world into darkness and cold. Had the asteroid landed in deep ocean or in less volatile terrain, the consequences might have been less severe. The choice of target Mexico's shallow shelf was a lottery of fate. Chicxulub was not just massive, it was perfectly placed to maximize devastation. Walking through the modern landscape, you would never suspect such violence. The crater is invisible, cloaked in vegetation and human settlement. Only its faint circle of cenotes, sinkholes formed where the crust collapsed, gives away the buried boundary. Tourists swim in their cool blue waters, unaware that these pools trace the rim of annihilation. It is a strange irony, a scar of death, repurposed as an oasis of life and leisure. To planetary scientists, Chicxulub is a Rosetta Stone. It shows what happens when worlds collide, how rock behaves at pressures higher than steel can withstand, how oceans vaporize, how climates tip in moments. For paleontologists, it is the crime scene where an empire ended. For all of us, it is a reminder that Earth's history is not a calm progression, but a series of jolts, moments when chance and chaos remake everything. The buried scar beneath the Yucatan speaks not only of what happened then, but of what could happen again. Near-Earth asteroids are tracked now with obsessive care, their orbits plotted to the decimal. Chicxulub is both a warning and a gift, a chance to learn from what the dinosaurs never saw coming. To study the crater is to stare into the abyss of chance, the knowledge that life on this planet can be rewritten in a single day. The stones under Yucatan tell us that the dinosaurs' world ended not in gradual twilight, but in a flash brighter than the sun, in shockwaves that shattered continents, in firestorms and famine that spread from a single point. Chicxulub is the X that marks the spot, the wound that explains the fingerprint in the clay, the scar that speaks for the silence of bones. It is hidden, buried, and yet it is everywhere, written into the very survival of our own kind. The asteroid came in at more than 20 kilometers a second, faster than a rifle bullet, faster than anything we can truly imagine. In the instant before impact, it was still silent, invisible against the morning sky, a mountain of stone wrapped in a sheath of flame. Then it struck, and silence ended forever. The Gulf of Mexico convulsed, as if the planet itself had been punched. In less than a heartbeat, the energy of billions of nuclear bombs detonated in a single spot, releasing heat so intense that rock turned to vapor and the sea itself exploded skyward. The Earth shuddered, shockwaves racing through the crust at supersonic speed, mountains trembling thousands of kilometers away. The blast crater yawned open, wider than London, deeper than Everest, is tall. For a few seconds, the ocean disappeared entirely, replaced by a fireball brighter than the sun. Everything within hundreds of kilometers, forests, rivers, entire ecosystems, was flash-fried in an instant. Rock that had been solid for hundreds of millions of years, liquefied, rebounded, and collapsed in molten waves, creating the peak ring buried beneath the Yucatan today. The very crust of the Earth rippled like water struck by a stone. From that fiery wound, debris shot into the upper atmosphere and beyond. Chunks of molten rock, blasted past escape velocity, arced into space before falling back across the globe. As they re-entered, they ignited the air. Imagine the sky itself on fire. Billions of glassy droplets raining down at hypersonic speeds, heating the atmosphere until it glowed red. Forests from North America to Asia burst into flame as if struck by an endless storm of meteors. Animals fled in vain. Herds of hadrosaurs and triceratops, already reeling from the thunder in the ground, were engulfed in firestorms that swept continents. The air became a furnace. In the oceans, the violence was no less apocalyptic. The impact generated a mega tsunami, waves taller than skyscrapers, rolling outward from the crater's heart. They surged across the Proto-Caribbean, sweeping sediment and creatures alike onto the land, then rebounded across the Atlantic and Pacific. Shorelines thousands of kilometers away were erased, coral reefs shattered, coastal forests drowned, entire marine communities obliterated in a single surge. Fossil evidence of these tsunamis' chaotic deposits of mixed shells, bones, and debris still lies buried along ancient coastlines, testimony to water turned into a weapon. Above the devastation, the sky turned into a lethal machine. The tiny glass spherules, molten droplets that had cooled into beads, rained down across the entire planet. They settled into rivers, lakes, and even the shells of marine plankton, marking that instant with microscopic precision. Each one carried the story of crustal rock melted and hurled into the heavens. To anyone alive at the time, the rain would have been terrifying glowing embers falling from a sky gone mad, igniting fields, suffocating forests, blotting out the stars. Then came the darkness, the fine dust and vaporized rock, rich in sulfur and soot, spread around the globe. Within days, sunlight dimmed to twilight. Within weeks, it vanished altogether. Temperatures plummeted as photosynthesis ceased. Plants withered, plankton collapsed, and food chains buckled. In the seas, ammonites and giant marine reptiles vanished. On land, the great dinosaurs, already stressed, could not endure. For them, there would be no recovery. What makes Chicxulub so chilling is not simply the scale of the impact, but the way every effect cascaded into the next. Shockwaves demolished, firestorms incinerated, tsunamis drowned, then darkness starved. No creature larger than a few dozen kilograms survived on land, save for those with the luck and physiology to endure long winters of famine. Burrowing mammals, seed-eating birds, crocodiles lurking in rivers, all had strategies that fit the catastrophe. Tyrannosaurs, triceratops, ankylosaurs, giants of an empire did not. Geological layers bear silent witness to this sequence of horror. Beneath the boundary, fossils teem with diversity. Above it, a barren silence broken only by survivors. In between lies the fingerprint of apocalypse. Shocked quartz, soot, iridium, glass spherules, tsunami deposits. It is a crime scene in stone, recording not just an impact, but a planetary execution. The planetary murder weapon was efficient not only in its energy, but in its timing. The asteroid struck shallow seas rich in sulfur-bearing limestone, releasing clouds of sulfuric acid that rained down and poisoned oceans. Had it landed in deep water or continental crust, the climate shock might have been less severe. Instead, it struck the worst possible place, amplifying destruction to a global scale. Chance, more than size, sealed the fate of the dinosaurs. To imagine it fully is to accept that the Earth itself can turn in an instant, that everything familiar can vanish between one sunrise and the next. For the dinosaurs, the last thing they saw was fire in the sky and darkness on the horizon. For the mammals cowering underground, it was the beginning of a long winter, but also of opportunity. Out of the smoke and silence, new life would one day rise. But for that moment, the planet itself was a weapon, and it had fired. The firestorms faded, the shockwaves ceased, and the tsunamis drained back to sea, leaving coastlines shattered and forests in ash. But what followed was worse than the violence of that single day. The asteroid had delivered not just a blow, but a wound that would not heal. Dust, soot, and vaporized rock hung in the stratosphere, spreading in a veil that wrapped the planet in shadow. The sun dimmed, the warmth drained, and a long winter began, not the gentle season of frost and snow, but an artificial night that lasted for years. For the dinosaurs who had survived the first hours of terror, it must have seemed like deliverance at first. The fires went out, the earthquakes stilled. Yet, as the days passed, the world refused to brighten. Noon felt like twilight. Leaves withered on trees that could no longer photosynthesize. Crops of cycads and conifers failed, and meadows that had supported herds of hadrosaurs turned grey. Insects searched for flowers that no longer bloomed. The chain of life cracked at its foundation, the green layer that sustained everything else. The oceans fared no better. Sunlight barely reached the surface, and the microscopic plankton that formed the base of marine food webs dwindled. Within weeks, entire species collapsed, their shells disappearing from the fossil record. Ammonites, the spiral-shelled drifters that had flourished for hundreds of millions of years, fell silent. The great marine reptiles that had hunted the mosasaurs and plesiosaurs starved in turn. Across the seas, famine spread like a contagion, working its way up through every link in the chain. The air itself became hostile. Sulfate aerosols from vaporized limestone mixed with soot from the global fires, creating acid rains that burned vegetation and poisoned rivers. Lakes turned sour, killing fish and amphibians. Soil chemistry shifted, making regrowth difficult even when seeds survived. Forests that had been the lungs of continents shrank into skeletal wastelands. The great herbivores, already weakened by hunger, had less and less to eat, while their predators found nothing to hunt. The winters blurred into years. Scientists who have modelled the climate suggest global temperatures dropped by as much as 20 degrees Celsius in some regions. For creatures evolved to warm, stable Cretaceous conditions, the sudden chill was a death sentence. Reptiles that relied on external heat struggled to regulate their bodies. Eggs failed to hatch in nests too cold to incubate life. Migration, hibernation, flight, none of the usual strategies mattered when the world itself seemed to have stopped. Above ground, the giants faltered. Tyrannosaurs, once rulers of their ecosystems, wasted away, their massive frames demanding more calories than the failing land could provide. Triceratops and ankylosaurs, armoured titans of the plains, staggered through barren landscapes in search of food that no longer grew. Even the smaller dinosaurs suffered. The delicate, feathered raptors, quick and clever, could not find prey in a world emptied of abundance. Their bones vanish from the record, within the same thin horizon as their larger kin. Below ground, in burrows and crevices, life persisted. Mammals, already practiced at surviving in the shadows, gnawed on seeds, roots, and the carcasses of the fallen. Crocodiles, amphibians, and turtles found refuge in rivers and ponds, insulated by water from the worst of the climate swings. Birds, descended from small feathered dinosaurs, weathered the famine by feeding on hardy seeds that could endure years of darkness before sprouting. Survival favoured not strength or size, but adaptability and frugality. The age of dinosaurs ended not with a battle, but with a starvation. Fossil evidence captures this silence. In layers immediately above the iridium clay, the variety of fossils shrinks dramatically. Diverse assemblages of species give way to monotony. Fern spores dominating the plant record. Fungi overwhelming pollen counts. Scientists call it the fern spike, a moment when opportunistic plants carpeted the wasteland, left by extinction. It was nature's reset button, the earth covering its scars with greenery as best it could. But for the dinosaurs, the reset came too late. They had already slipped into history. For 5 years, the planet stayed dim, a twilight earth, where days bled into one another, where nothing grew fast enough to feed the hungry. For smaller, more resourceful creatures, those years felt endless but survivable. For the dinosaurs, they were eternity. Evolution does not pause for sympathy. In a few geological heartbeats, entire lineages that had ruled the earth for 150 million years were gone. When the skies finally began to clear and the sun returned, it shone on a transformed planet. The air warmed, forests regrew, rivers flowed clean again. But the old rulers were missing. Their absence created a vacuum into which mammals, birds, and others would expand. The age of reptiles was over. The stage belonged to a new caste. The 5 bad years were not the longest winter the earth would ever see, but they were among the most consequential. They proved that survival was not about dominance, but endurance. The asteroid had not killed everything, but it had rewritten the rules. The dinosaurs had lived large, and they died large. Those who lived small, who hoarded seeds, who burrowed, who waited, stepped blinking into the light of a new world. In those years of twilight and famine, the earth revealed a cruel truth. Life can be fragile, toppled by a single blow. Yet it also revealed resilience, the stubborn persistence of creatures who endure even when the skies themselves seem to have gone dark. The dinosaurs were gone, but life itself had survived the longest night, ready to begin again. Long before the asteroid flared across the Cretaceous sky, the Earth was already trembling. Deep beneath what is now Western India, a wound in the planet's crust had torn open, and from it poured fire. Not a single volcano rising like Vesuvius or Fuji, but a vast province of fissures stretching for hundreds of kilometers, bleeding molten rock in eruptions so immense they defy imagination. Over the span of nearly 1,000,000 years, wave after wave of lava surged across the land, hardening into black basalt plateaus stacked like layers of a colossal cake. Today we call it the Deccan Traps, after the Dutch word for stairs, because from a distance, the stepped cliffs of ancient flows resemble a giant staircase built by gods or monsters. In truth, it was Earth's own fury, a planetary convulsion that flooded half a continent in fire. The scale is almost incomprehensible. At its peak, the Deccan eruptions spewed enough lava to bury all of France under a kilometre of molten rock. Some pulses may have lasted decades, with fountains of lava surging night and day, rivers of fire, hundreds of kilometres long, carving new landscapes. Ash clouds darkened skies across regions. Acid rains scorched forests, and ecosystems faltered even before the asteroid entered the story. The dinosaurs were living on a planet already destabilized, its thermostat twisting wildly out of balance. But the rock is only half the tale. What mattered most to the climate was invisible. With every eruption came staggering volumes of gases: carbon dioxide, sulfur dioxide, methane, water vapor. Together, they rewrote the atmosphere. Carbon dioxide trapped heat, driving intervals of global warming that baked ecosystems, wilting plants and stressing animals already adapted to steady climates. Sulfur, conversely, cooled the Earth, its aerosols scattering sunlight and plunging regions into chill. The result was chaos, swings from sweltering heat to sudden cold, whiplash shifts that stressed food webs to breaking. One pulse of eruptions could trigger decades of searing drought. The next could blanket the skies in haze, dimming the sun and freezing rivers. Life does not thrive in instability. Evidence of this volcanic violence survives in sediments worldwide. In the 1,000,000 years before the asteroid impact, fossil pollen records show forests thinning and shifting, plants adapting to strange seasons that did not align with ancient rhythms. In the oceans, the microscopic shells of plankton record chemical chaos, carbon levels spiking and falling, oxygen sagging as waters struggled to breathe. Extinction rates among marine creatures rose long before the asteroid struck, hinting that the stage for catastrophe had already been built. The Deccan Traps were not merely eruptions, they were engines of global disruption, a slow-motion apocalypse that weakened ecosystems one blow at a time. Some scientists argue that without the Deccan eruptions, the asteroid might not have finished the dinosaurs so completely. The volcanic gases, they suggest, had already nudged the Earth to a precarious edge. Food webs were stressed, populations declining, diversity shrinking. The asteroid's blow was lethal because the patient was already sick. Others argue the opposite, that the asteroid's impact may have accelerated the volcanism itself. Seismic shockwaves from Chicxulub could have rumbled through the Earth, stirring the magma chambers beneath India, intensifying eruptions just when the biosphere least needed another insult. In this view, asteroid and volcano were conspirators, not rivals, a 1-2 punch that left no room for recovery. Walking the Deccan Plateau today, you tread on the relics of that violence. Layer after layer of basalt stretches to the horizon, stair-stepped cliffs rising into hazy skies, carved by rivers and monsoons, but still bearing the mark of fire. Geologists can date each layer, reading the tempo of eruptions, the pauses and surges. Some flows are thin, mere trickles compared to others, giant sheets, dozens of meters thick, that speak of flood events on a continental scale. The rock is silent, yet within its chemistry lie the ghosts of gases that once choked the skies, rewriting climates and altering the trajectory of evolution. The dinosaurs living in that world must have sensed the change. Herds of hadrosaurs grazing floodplains saw plants wither in drought and vanish in cold snaps. Predator and prey alike grew leaner, their bones recording stress. Insects, ever sensitive to climate, swarmed in some places, vanished in others. Migration routes that had endured for ages became perilous as weather turned unpredictable. To the animals of the Cretaceous, these shifts must have felt like a curse, a world unravelling not in a day, but across lifetimes. The Deccan traps remind us that extinction is rarely a single moment. It is a process, a long erosion of stability, punctuated by catastrophes that seal the fate. Whether the dinosaurs might have endured the volcanism alone is impossible to know. Some lineages may have persisted, adapting to warmer, harsher climates, just as life had endured earlier mass extinctions linked to volcanism. But with the asteroid's arrival, the question became moot. The world was already weakened, its lungs filled with volcanic fumes, its climate staggering like a fevered patient. The asteroid did not strike a healthy planet, it struck one already gasping. To call the Deccan eruptions volcanoes is almost misleading. They were not singular mountains, but a planetary system convulsing, a breach in the crust through which the mantle itself poured out. In some places, lava surged so fast it may have travelled across the landscape at highway speeds, incinerating forests and rivers in minutes. The noise would have been deafening. A constant roar, like 1,000 jet engines, punctuated by explosions that hurled ash into the stratosphere. For creatures living nearby, survival was a daily miracle. The irony is that in the long term, the Deccan traps created some of the most fertile soils on Earth. Basalt, once weathered, is rich in nutrients. Today, the plateau sustains agriculture that feeds millions. Life always finds a way to repurpose ruin, but in the late Cretaceous, the eruptions were not a gift. They were a slow strangling, a planet's own fire turned against its inhabitants. So when we ask why the dinosaurs died, the answer is not simply an asteroid. It is fire from above and fire from below. It is skies darkened by soot and skies poisoned by sulfur. It is ecosystems battered first by volcanic fever, then obliterated by cosmic impact. The Deccan traps were already roaring when Chicxulub arrived, and together they ensured that the age of dinosaurs ended not with a whimper, but with a world turned inside out. The rocks remember in ways we cannot. They carry whispers of poisons that once drifted on the wind, of rains that scalded the earth instead of nourishing it, of forests burned not by flame but by chemistry itself. To walk the layers of the late Cretaceous is to trace not only bones and ash, but the invisible hand of toxins, spread wide across land and sea. One of the strangest breadcrumbs is mercury, a metal most of us know from broken thermometers and warning labels. Yet, in the geological record, its presence tells a story of volcanic fury, of the Deccan traps, breathing poison into the sky and leaving their fingerprints across the globe. Mercury does not belong in abundance in sedimentary rocks. It is rare in Earth's crust, easily dispersed, and usually too diluted to notice. But when volcanoes erupt, particularly the monstrous kind that define the Deccan traps, they release mercury vapor in staggering quantities. It floats high into the atmosphere, travels the winds, and eventually rains down, binding itself into soils, clays, and ocean sediments. The late Cretaceous layers show repeated spikes of this toxic metal, each aligned with pulses of lava from India. To geologists, These spikes are timestamps, markers of planetary stress. They confirm that eruptions were not only local spectacles, but global events. Their reach measured not in kilometers, but in continents. The implications for life were devastating. Mercury, in small doses, can damage nervous systems, disrupt reproduction, and poison food chains. In the oceans, mercury settles into plankton, climbs into fish, and cascades upward into predators. For ammonites and mosasaurs, these invisible toxins may have weakened populations long before the final asteroid blow. On land, plants absorbed mercury into their tissues, passing it to herbivores, which in turn passed it to carnivores. The system was unraveling not just from climate chaos, but from chemical sabotage. The same eruptions that delivered mercury also seeded the skies with sulfur. When sulfur dioxide mixes with water vapor, it becomes sulfuric acid, and from those poisoned clouds fell rains that scalded leaves, burned soil, and turned lakes into cauldrons of acid. Imagine a hadrosaur herd moving through what should have been lush wetlands, finding instead pools so sour they stripped bark from fallen branches and left fish floating belly up. The forests that survived the fires of lava faced this slow chemical assault, their roots choking in altered soils. The fossil record reveals abrupt shifts in plant communities, with some lineages vanishing while hardier, more acid-tolerant species gained ground. For the creatures of the Cretaceous, these changes came as an invisible thief in the night. There were no roaring flames or crashing waves, just the slow erosion of vitality. Eggshells thinned, hatch rates declined, predators grew leaner as prey animals weakened. Mercury and acid rain may not leave skeletons like a tyrannosaur does, but their legacy is etched in the absence, in the sudden gaps in diversity, in ecosystems struggling even before the asteroid came. The sediments of ancient oceans give the clearest testimony. In cores drilled from seabeds, mercury spikes line up like beats in a drum, echoing the pulses of Deccan volcanism. Each spike marks not just lava flowing across India, but global fallout poison settling into waters thousands of kilometers away. In those same layers, carbonate shells of plankton grow thinner, evidence of ocean acidification, driven by both volcanic CO2 and acid rain. It is a chemical double punch, mercury undermining physiology, while oceans turned corrosive around the very creatures that built the base of the food chain. When the asteroid finally struck, the world was already compromised. The impact delivered fire, shock, and darkness, but the biosphere had been absorbing toxins for hundreds of thousands of years. Like a patient already weakened by disease, life had fewer defenses. The great reptiles and their ecosystems were not toppled by a single push. They were poisoned, scorched, starved, and finally struck down. Today, the Deccan Traps stand silent, their vast, stair-stepped cliffs weathered by monsoons and threaded with fields. But in those rocks lies the record of a planet gone haywire. Geologists studying mercury concentrations in sediments from Italy, China, and North America find the same story. Plumes of toxic vapor that encircled the Earth. These were not isolated burps of fire, but sustained emissions that reshaped climates and poisoned air, water, and land. The story of extinction is not just a tale of sudden catastrophe, but of long poisoning, of life slowly suffocating under the breath of a restless planet. It is sobering to realize how subtle these killers were. Dinosaurs might have adapted to warmer climates, even to erratic seasons, but no creature can thrive when its very food is tainted. A mother triceratops might lay eggs only to find her hatchlings too weak to live. A pterosaur might scour the skies for fish, only to find seas drained of vitality. The great predators might stalk the plains, their strength faltering as their prey grew scarce. By the time the asteroid painted the skies with fire, the poisons had already hollowed out the world. Mercury in the rocks, acid in the rains, sulfur in the clouds. These are the whispers of catastrophe, the invisible forces that worked alongside fire and stone. They remind us that extinction is not always a roar. Sometimes it is a toxin in the blood, a slow corrosion that eats away at resilience until one final blow ends it all. The dinosaurs walked a poisoned earth long before they vanished, and the rocks still remember. The continents were never still, even in the age of dinosaurs, beneath the forests of Triceratops and the swamps of hadrosaurs. The planet's crust creaked and shifted, reshaping the stage on which the great reptiles played out their final acts. By the late Cretaceous, the world had already changed from the one their ancestors had inherited. Once, shallow seas had stretched like warm, sunlit highways across continents, teeming with fish, ammonites, and marine reptiles, providing humid coastlines where dinosaurs thrived. But as the tectonic plates drifted and collided, those seas drained away, coastlines retreated, and the mosaic of habitats began to fragment. The great inland seaways that had once made North America a patchwork of islands shrank into muddy estuaries and eventually dried into prairie. For creatures adapted to lush deltas and endless coastlines, the world was becoming smaller, harsher, and less predictable. The Western Interior Seaway, a vast body of water that once split North America from the Gulf of Mexico to the Arctic, was perhaps the most dramatic example of this tectonic rearrangement. For millions of years, it had been a paradise, shallow, warm, rich in nutrients, a nursery for marine life, and a hunting ground for mosasaurs and plesiosaurs. Its coastlines supported forests and plains where hadrosaurs and ceratopsians flourished, while pterosaurs skimmed the waters and left their shadows across the beaches. But as mountain ranges rose to the west and global sea levels fell, the seaway retreated. By the final million years before the impact, it had narrowed to ribbons and lagoons. No longer the vast inland ocean it once was. With its disappearance, entire ecosystems collapsed, forcing animals into tighter, less diverse habitats. South America, too, was drifting away, its once close ties to Africa severed by the widening Atlantic. India was on a collision course with Asia, racing northward on the currents of mantle convection. As it sped toward its future, crash into the Himalayas, it carried with it the Deccan traps, spewing lava and gases into the atmosphere. Antarctica, still forested in the Cretaceous warmth, began its slow slide toward isolation at the South Pole. Each shift altered currents, climates, and coastlines. The dinosaurs did not understand the deep physics of plate tectonics, but they felt its consequences. Changes in rainfall, altered migration paths, vanished feeding grounds. The Earth was redrawing its map beneath their feet. These tectonic motions reshaped sea levels worldwide. During much of the Cretaceous, oceans had flooded continental margins, creating shallow seas ideal for biodiversity. But toward the end, global sea levels dropped by as much as 100 meters in some regions. Continental shelves that had been drowned were exposed, transforming shallow marine nurseries into barren coastal plains. Coral reefs, once thriving along flooded coasts, withered as waters receded. Marine reptiles lost hunting grounds. Birds lost fishing shoals, and countless invertebrates that had flourished in shallow, sunlit waters vanished. On land, the loss of coastal wetlands reduced the diversity of plants and the herbivores that depended on them. The fragmentation of habitats was subtle compared to the asteroid's sudden violence. but in evolutionary terms, it was deadly. Species that had once roamed vast, connected environments now found themselves trapped in shrinking pockets. Isolation breeds vulnerability. A drought here, a volcanic winter there, and an entire lineage could disappear, with no neighbouring population to replenish it. Dinosaurs that had once been rulers of continents found themselves prisoners of geography. Herds that once migrated freely were hemmed in by new deserts or receding seas. Predators, deprived of their wide hunting grounds, struggled to adapt to smaller ranges. The fossil record reflects this fragmentation. In the last million years of the Cretaceous, diversity in some groups was already declining. Fewer species of large herbivores appear, suggesting shrinking ecosystems that could no longer support the same variety. Some clades, like certain hadrosaurs, flourished briefly in local pockets, but never regained their earlier abundance. Marine fossils tell a similar story. Ammonites became less diverse, their shells scarcer, even before the final boundary layer sealed their fate. The tectonic shifts had not yet killed the dinosaurs, but they were steadily narrowing their world. Climates, too, shifted with the continents. The retreat of shallow seas meant less moderation of seasonal extremes. Where once a vast inland ocean had kept summers humid and winters mild, now heat waves scorched and cold snaps bit harder. For creatures accustomed to relatively stable conditions, such fluctuations were disruptive. Rainfall patterns changed, droughts lengthened, monsoons failed. Plants bore the brunt of these swings. And as the flora faltered, so too did the animals that depended on them. The interconnected web of the Cretaceous was already fraying when the asteroid appeared in the sky. To imagine this slow unravelling, think of the dinosaurs' world as a great stage play. For over 150 million years, the set had been stable, the props familiar: lush forests, broad plains, endless seas. Then, in the final act, stagehands began dismantling the scenery. The forests shrank, the seas drained, the coastlines retreated. The actors, tyrannosaurs, triceratops, hadrosaurs, continued their performances, unaware that the stage itself was collapsing beneath them. They were not yet doomed, but they were vulnerable, and vulnerability is what catastrophe feeds upon. When the asteroid struck, it did not fall on a paradise of endless abundance. It fell on a planet already in transition, where continents were shifting, seas were vanishing, and ecosystems were stressed. The violence of impact was decisive, but the groundwork had been laid by the slow grinding of plates and the lowering of seas. The Cretaceous world was in flux, and its rulers were less secure than they appeared. The irony is that the very tectonic movements that stressed the dinosaurs paved the way for the world that came after. The retreat of seas opened up land for mammals to expand into. India's northward flight would eventually raise the Himalayas, altering climate and circulation for millions of years to come. The Atlantic's widening created new coastlines, new opportunities, new ecological frontiers. Out of the disintegration of the old world, the seeds of the new were sown. But in those last Cretaceous years, none of that mattered to the dinosaurs. What they felt was scarcity where there had been plenty, instability where there had been balance. The Earth itself was turning against them, not with one sudden strike, but with a slow rearrangement of continents and seas. By the time the asteroid arrived, the world of the dinosaurs had already begun to slip away. The blow from the heavens was final, but the tectonic engine beneath their feet had been preparing the stage for extinction all along. By the twilight of the Cretaceous, dinosaurs had been the lords of Earth for more than 150 million years. Their dominion seemed absolute, but if you look closely at the record left in bones and teeth, in nests and footprints, you can sense the strain of an empire At high noon, brilliant and commanding, yet stretched to its limits. Diversity still abounded, but cracks were forming beneath the surface. Subtle signs that the giants were living at the edge of what their bodies and their ecosystems could sustain. The great plant eaters, the hadrosaurs and ceratopsians, filled the plains in vast herds. Their skulls grew ever more elaborate, crests and frills blooming like armour forged into carnival displays. These extravagant forms, dazzling to behold, were not signs of strength, but of specialisation, adaptations for mating displays, social bonding, or species recognition. Specialisation, though, is a double-edged sword. In stable times, it can help a lineage thrive, but when climates shift or habitats shrink, it can leave them vulnerable. A triceratops could dominate its prairie when grasses and cycads were plentiful, but when drought-withered plants or ash-darkened skies, its rigid feeding habits and colossal appetite became liabilities. The predators, too, were straining under the weight of their own magnificence. Tyrannosaurs, sleek in form and terrible in power, had become apex specialists, their massive skulls engineered for bone-crushing bites, their senses tuned to track herds across open country. Yet their very size demanded enormous amounts of prey, more than a stressed ecosystem could reliably provide. Fossils of tyrannosaurs show signs of starvation in juveniles. Bones thinned, growth stunted. For such predators, any disruption in the chain of abundance meant catastrophe. Reproduction, always the quiet engine of survival, tells another story of fragility. The larger the dinosaur, the more costly its strategy. Giant sauropods had long ago perfected the tactic of laying vast clutches of small eggs, flooding the odds with numbers. But by the end of the Cretaceous, sauropods were rare outside of South America, their once globe-spanning dynasty reduced to a handful of lineages. The horned and duck-billed giants of the north laid fewer eggs and took longer to mature, betting on stability that no longer existed. When environments turned erratic and catastrophe struck, their reproductive strategies could not recover quickly enough. Mammals, in contrast, bred in burrows, raised small litters, and could bounce back in years. Dinosaurs needed decades to restore what a single disaster could erase overnight. Some smaller dinosaurs were diversifying into niches that hinted at the future. Feathered raptors hunted in forests, nimble and quick, their bodies covered in down that suggested a resilience to climate swings. Early birds, already capable of seed diets and wide-ranging flight, showed traits that would carry them across the extinction boundary. But these were exceptions. The majority of dinosaur clades were giants, tied to specific ecosystems, invested in forms and habits that made them vulnerable to sudden change. The fossil record of the last million years of the Cretaceous hints at this unevenness. Some regions show bursts of diversity horned dinosaurs in western North America, proliferating into numerous species, each with its own frill and horn arrangement. Yet in Asia, other lineages declined, their fossil traces dwindling. It is as if the dinosaurs' golden age had fractured into local triumphs and global decline. High noon, blazing brilliance, but shadows already stretching long. Even in their magnificence, dinosaurs were paying the price of being colossal. A triceratops could weigh as much as a truck, consuming hundreds of pounds of vegetation daily. A tyrannosaur needed constant access to prey herds the size of small towns. Such scales of appetite meant that when disruptions came, whether from volcanic winters, poisoned rains, or retreating seas, their sheer bulk turned from advantage to burden. In stable ecosystems, size is dominance. In chaos, it is hunger. The irony is that dinosaurs were not weak in the sense of decline. They were still everywhere, filling forests, plains, and river valleys with their presence. But they were locked into roles too rigid to bend when the world shifted under them. They had pushed their evolutionary strategies to their zenith. And zeniths, by definition, cannot be sustained forever. High noon glows brightest just before the evening descends. Had the asteroid missed, perhaps some lineages might have endured, adapted, and branched into new forms. Yet the signs of strain suggest they would have faced a harder road than their ancestors had enjoyed. The costs of being colossal, of reproducing slowly, of specializing too finely, had left them exposed. When catastrophe arrived, it did not strike a world of limitless resilience. It struck a dynasty already balanced precariously on the weight of its own grandeur. The bones whisper this story to us. They show us growth rings like trees, marking stunted years. They show us nests abandoned mid-season, embryos that never hatched. They show us predator teeth etched with hunger, herbivore bones with signs of malnutrition. They are not the records of failure, but of strain creatures still thriving, yet pushed to their limits by a planet reshaping itself beneath them. At high noon, the dinosaurs stood proud, their horns gleaming, their roars echoing across continents. But noon is a moment, not an eternity, and in that moment, as tectonics shifted, volcanoes roared, and skies grew unstable, the lords of Earth were already walking the edge of twilight. When the world dimmed and the forests burned, survival did not belong to the mighty. It belonged to the quick, the adaptable, and the overlooked. While titans like Triceratops and Tyrannosaurus stalked their last days under fading skies, it was the scurrying mammals in their burrows and the small, feathered dinosaurs perched in the canopy who carried the thread of life across the abyss. The catastrophe did not ask who had ruled the longest. It rewarded those who could bend, hide, and wait. Warm-bloodedness, once a costly luxury, became an art. To burn calories constantly, to keep the body warm through night or cold snap, is demanding when food is abundant. But when the skies were veiled in ash and the climate plunged into chaos, the ability to regulate body heat gave mammals and birds a chance where reptiles faltered. Crocodiles could survive too, but only by retreating into rivers and slowing their lives to a crawl. Mammals could huddle underground and still emerge to forage. Birds, with feathers that trapped warmth, could weather the chill long enough to find seeds hidden under snow and ash. Diet, too, was a decisive factor. The giants of the Cretaceous were specialists, hadrosaurs grinding cycads and conifers, tyrannosaurs built for massive prey. Their size demanded consistency. Mammals and many birds were generalists, nibbling seeds, insects, roots, carrion. When the food web collapsed from the bottom up, the generalists found substitutes. A rodent-sized mammal could scrape by on beetle larvae in rotting wood or dig tubers from a frost-bitten soil. A crow-sized bird could pick clean a carcass one day and crack seeds the next. Variety became resilience, and resilience became survival. Reproductive strategies magnified the advantage. A triceratops needed years to raise a calf to adulthood, each investment fragile in a time of scarcity. Mammals could produce litters, their young nurtured by milk even when the outside world failed. Birds laid small clutches and fledged their offspring quickly. Shorter generation times meant faster recovery when populations dipped. Evolution favors those who can adjust swiftly, and in the shattered landscapes after the impact, speed was everything. Burrows and nests were refuges as much as homes. When firestorms raged across continents, when the first weeks after impact turned forests into infernos, small creatures underground avoided the flames. Fossil burrows from the late Cretaceous and early Paleogene show that mammals were already masters of living below the surface, digging into safety while predators thundered above. Birds that could nest in cavities or flee on wings had choices unavailable to the earthbound colossi. Adaptations born of daily survival suddenly became shields against global catastrophe. Even physiology itself tilted the odds. Small animals need less food, less space, less of everything. In lean times, a shrew-like mammal could survive on crumbs that would not have satisfied a hatchling triceratops. Birds with efficient respiratory systems, breathing more deeply and fully than any reptile, could endure thinner, smoke-choked air. Where the giants needed stability, the small thrived in instability. The fossil record of the earliest Paleogene tells the story starkly. While the dinosaurs vanish almost entirely above the boundary line, mammal fossils explode in number and variety just a few 100,000 years later. Rodent-like multituberculates, primate ancestors, hoofed proto-mammals, all began to radiate into the niches left empty by the vanished lords. Birds, too, diversified rapidly, their lineages seeding the skies with songbirds, raptors, and waterfowl. The survivors did not merely endure. They adapted, expanded, and claimed the new world as their own. This was not inevitable. Catastrophe is always a lottery. Its winners and losers determined by circumstance as much as by design. Many mammal lineages perished. Many bird groups fell silent, but enough endured, because their bodies, habits, and choices gave them tools the giants lacked. In darkness and famine, the meek inherited the earth, not by strength but by flexibility. The story of survival after the Cretaceous is not just about who lived and who died. It is about the qualities that make life endure when the rules of the game change without warning. Warm blood, varied diets, short generations, small size, protective shelters. These were the seeds of survival, planted long before the skies fell. The asteroid did not create resilience. It revealed it. In the stillness after the firestorms, the Earth must have seemed haunted. The roars and trumpets of dinosaurs were gone, replaced by the quiet scratching of mammals in the underbrush, and the tentative calls of birds probing the silence. A world once ruled by giants had been handed to creatures light enough to hide in the cracks. From those cracks, a new story would grow. Survival is rarely glamorous. It is messy, humble, often invisible. The mammals and birds that outlasted the cataclysm did not look like victors. They looked like scavengers, opportunists, desperate stragglers. Yet from their persistence came every songbird in the morning sky, every human being reading these words. The seeds of survival, scattered in the ash of the dinosaurs' world, would bloom into an entirely new age. The lesson is plain. Dominance does not guarantee endurance. Adaptability does. And in the crucible of extinction, it was the small, the nimble, and the resourceful who found a way through the dark. In the ash-choked silence after the impact, when flames had devoured forests and smoke blotted out the sun, one form of life rose to prominence with eerie speed. It was not the mighty reptiles who had ruled for ages, nor the mammals biding their time in the shadows, but a kingdom, older still, fungi. The fossil record preserves their triumph in a signal so distinct it has a name, the spore spike. Across layers of rock that mark the boundary between the age of dinosaurs and what came after, microscopic spores proliferate in quantities unmatched before or since. The earth, stripped bare and smothered in death, had become a paradise for decay. Forests, once vast and green, were reduced to blackened skeletons. Trees that had shaded herds of triceratops and resonated with the calls of hadrosaurs stood charred or toppled, their bodies lying as endless fuel. Ash settled over the land, mixing with rain to form sludge that coated soil and choked rivers. Animals too had fallen in staggering numbers. Whole herds, caught in firestorms, lay where they died. Oceans were littered with carcasses of ammonites and marine reptiles. It was a planet of carrion and rot, and fungi, opportunists of decomposition, surged into the void, left by life undone. The biology of fungi made them perfect heirs to this apocalypse. They need no sunlight to thrive, only organic matter and moisture. With photosynthesis collapsed, plants withering in the darkness, and food webs unraveling, fungi faced no such limitations. They spread hyphae into dead wood, into carcasses, into soil enriched with ash and decay. Their spores rode the wind, filling the air, settling into every crevice. In lake sediments from this time, the layers are packed with their microscopic remains, tiny fingerprints of a world where mushrooms and moulds had seized the upper hand. It is difficult to imagine the visual transformation, but the planet might have looked like a fungal bloom on a titanic scale. Forest floors carpeted not in ferns or flowers, but in eruptions of fruiting bodies, sprouting from charred logs. Corpses softened, then dissolved, as white threads spread through muscle and bone. Even the shells of turtles and the armour of ankylosaurs, once seemingly impervious, provided footholds for decay. The air must have been thick with the earthy tang of rot, spore-laden and humid in the dim light that filtered through soot and dust. For the survivors, this bloom was both curse and salvation. On one hand, spores could choke lungs, and fungal infections might have spread in stressed animal populations already weakened by hunger. On the other, fungi recycled nutrients back into devastated ecosystems, breaking down the wreckage of the old world and preparing the soil for the new. Without them, the return of forests might have taken far longer, the land locked under layers of dead matter. Instead, fungi made way for regrowth, clearing space for seedlings that would emerge once sunlight returned. The spore spike is not just a curious detail, it is evidence of the scale of destruction. Only when death is nearly universal do decomposers dominate so completely. It testifies to a biosphere reduced to its most basic cycle. Life into death, death into decay, decay into soil. For perhaps years after the impact, the Earth was less green than grey, less a living planet than a compost heap on a planetary scale. Yet within this dominion of rot lay the seeds of renewal. The first plants to return after the impact were hardy pioneers' ferns, which spread quickly in disturbed soils. Paleobotanists call it the fern spike, a rebound recorded in layers just above the fungal bloom. But ferns could only reclaim the earth because fungi had first scoured it clean, breaking down the charred remains that littered the land. The succession from fungi to ferns to forests illustrates nature's resilience, the way destruction creates its own path to recovery. There is a dark poetry in this episode. Dinosaurs, the monarchs of the Mesozoic, ended not in fiery glory, but in quiet dissolution, their remains feeding the rise of organisms too small to see without magnification. The reign of giants gave way to the reign of rot. Fungi cared nothing for power or dominance. They consumed impartially, turning tyrants and prey alike into the same fertile soil. In that impartiality lies their power. Even today, echoes of that ancient bloom linger. Modern fungi carry genetic lineages that stretch back through those years of dominance, proof of their adaptability in the worst of times. They remind us that survival is not always about strength or speed or cleverness. Sometimes it is about waiting in the soil, ready to rise when catastrophe sweeps everything else away. The spore spike is a record of collapse, but also of transition. It tells us that the age of dinosaurs ended in a world defined by decay, but it also marks the beginning of a recovery driven by life's most patient recyclers. The forests that regrew, the mammals that spread, the birds that filled the skies, all of them were nourished by the great fungal bloom that feasted on extinction and turned it into fertility. The world that emerged from that dark age would be different, smaller at first, but alive again. And at its foundation was the silent, ceaseless labour of fungi, thriving where everything else had failed, proving that even in the deepest ruin, life finds a way forward through rot, through spores, through the quiet power of decay. Beneath the surface of the world's oceans, where sunlight filtered down through clear blue water and plankton bloomed in countless billions, the real heartbeat of the earth once pulsed. Every wave that lapped a Cretaceous shoreline, every storm that rolled across an inland sea, drew its energy from a system powered by these microscopic organisms. Calcifying plankton, tiny coccolithophores and foraminifera built delicate shells from calcium carbonate, drifting in endless swarms, feeding larger plankton, which fed small fish, which in turn fed the marine reptiles and seabirds that ruled the coasts. It was a chain of life as old as the Mesozoic itself, resilient through eons of change. But when the asteroid struck, the ocean's heartbeat faltered, and then it stopped. The violence on land is easier to picture: forests burning, dinosaurs collapsing under ash-darkened skies, but in the oceans, the catastrophe was no less complete. The blast had vaporized limestone and sulfate rock, throwing sulfur dioxide and carbon dioxide high into the atmosphere. When this mixed with rain, the result was acid that fell back into the seas. Carbonate chemistry, finely balanced over millions of years, was jolted into chaos. The water became undersaturated with respect to calcium carbonate. In plain words, it could no longer support the tiny shells that had long been the foundation of marine ecosystems. Plankton that had once built intricate lattices of calcite now found their shells dissolving as soon as they formed. Fossil records bear silent witness. In the layers just below the impact horizon, coccolith plates are abundant, forming thick chalk beds that gave the Cretaceous its very name. Immediately above, they nearly vanish. The ocean, for a geological moment, lost its most prolific architects. Without them, the food chain began to collapse from the base upward. Tiny fish that fed on plankton starved, larger predators starved in turn. Mosasaurs, plesiosaurs, and ammonites, the icons of Cretaceous seas, faded rapidly from the record, not because they were directly burned by firestorms or struck by debris, but because their food supply evaporated. An ocean without plankton was an ocean without a pulse. The knock-on effects reached far beyond the water. Much of Earth's carbon cycle depends on the rain of dead plankton to the seafloor, where their shells lock away carbon in layers of sediment. Without them, atmospheric carbon dioxide stayed higher, climate recovery slowed, and nutrient cycling on land faltered. Rivers carried minerals to the sea, but with no plankton to trap and recycle them, the nutrients washed out into dead zones. Coastal ecosystems that had once been fed by upwelling currents found themselves starved. Forest regrowth slowed, soil fertility lagged, and the land itself felt the silence of the seas. Imagine a world where the ocean had turned ghostly clear, stripped of the milky haze that plankton normally give it. Sunlight would have penetrated deeper, but found little to nourish. Shoals of fish would have dwindled to nothing, their predators left to wander empty waters. For years, perhaps decades, the seas were less living environments than vast saline deserts. The fossil record even suggests that only a handful of plankton lineages scraped through, clinging on in isolated refuges, waiting for chemistry and sunlight to rebalance. And yet, even in this silence, life adapted. Non-calcifying plankton, which relied on organic shells or none at all, took advantage of the collapse. Dinoflagellates, with their strange flagella and flexible walls, proliferated in some regions, seeding future ecosystems. Some lineages of coccolithophores managed to evolve thinner, more dissolution-resistant shells. A few foraminifera endured in sheltered lagoons, where conditions were less corrosive. These survivors formed the genetic seed stock from which future oceans would recover, but recovery was slow, stretching across tens of thousands of years. On land, this gap in the ocean's productivity translated into famine for creatures that had depended on marine food webs. Seabirds, already among the most adaptable of dinosaurs, faced population bottlenecks as fish supplies dwindled. Marine reptiles had no such fallback. They vanished almost entirely. Even mammals that hunted the coasts or scavenged beaches would have felt the pinch. The ocean was not just background scenery, it was the Earth's circulatory system, and when it faltered, everything connected to it faltered too. The death of calcifying plankton also changed the geology of the Earth. With fewer shells sinking, fewer chalk beds formed. The sedimentary record of the early Paleogene is marked not by thick, white limestones, but by darker clays, poor in carbonate. It is as if the ocean stopped writing its history in chalk and switched to ink. These thin, dark layers, the boundary clays, mark a pause in the grand deposition of carbonates that had characterized much of the Mesozoic. Even the Earth's rocks carry the signature of a world that had lost its marine pulse. When recovery finally came, it was uneven. Some plankton radiated explosively into the empty niches, evolving new forms and strategies. Within a few million years, the seas were once again alive with chalky rain, coccolith plates drifting down to the abyss, rebuilding the carbon cycle. But for those crucial first years after the impact, the absence was total enough that ecosystems on both land and sea were stripped to their foundations. What the fossil record tells us, then, is that extinction was not just a story of dinosaurs falling on land. It was also a story of oceans hollowed out, their energy circuits broken. The collapse of calcifying plankton severed the arteries that had carried life across the planet. When the seas starved, the land followed. In that silence, mammals and birds eked out survival, fungi bloomed, and forests slowly returned. But the ocean, the true engine of the biosphere, took longer to recover, leaving behind a world where life's rhythms had been broken. To call it an ocean without a pulse is no metaphor. It is a literal truth, preserved in sediments that show a sudden vanishing of the heartbeat of marine life. For a time, the seas were quiet graves, stripped of their tiny architects. Only when they returned did Earth's breath steady again, carrying forward the survivors into a new age. There are few places on Earth where time itself seems to have stopped, where catastrophe has been pressed into stone so perfectly that it feels less like paleontology and more like crime scene investigation. Tanis, a site in North Dakota, is one of them. Here, in a layer no thicker than a few meters, lies the frozen moment when the age of dinosaurs ended not millions of years of slow decline, not centuries of fading fortunes, but minutes and hours after the asteroid struck. Every shovel of earth turned at Tanis brings up whispers of chaos, as if the riverbed itself still holds its breath from that terrible day. The story begins not with dinosaurs, but with fish, paddlefish and sturgeon, creatures little changed since the Cretaceous, are stacked like cordwood in the sediment, their bodies tangled, their death sudden. Their gills are packed with glass spherules, tiny beads of molten rock that rained from the sky after the Chicxulub impact blasted Earth's crust into vapor. These spherules cooled as they fell, solidifying into glass before they hit the ground, or, in this case, the water. The fish breathed them in and suffocated, choking on fallout from an explosion 2,000 kilometers away. There is no clearer fingerprint of the catastrophe. Yet the story does not stop at the gills. The fish are arranged in layers that suggest violent surges of water, back and forth, as if the river had been shaken like a bowl. These were Seishi waves, not the result of local storms, but of seismic shock. When the asteroid struck, it sent a pulse through the Earth's crust, a jolt so massive it travelled faster than sound through stone. Hours later, that shock reached the interior of the continent, sloshing rivers and lakes, stacking fish and sediment in chaotic heaps. At Tanis, it was enough to bury thousands of animals alive. Mixed into this bedlam are the scattered remains of other creatures, fragments of dinosaurs, disarticulated but fresh, hint at bodies torn apart in the flood, teeth from small mammals, shells from freshwater invertebrates, even insects caught mid-flight, everything trapped in the slurry of sand and spherules. One layer contains tree trunks charred by fire, swept into the river along with the still green leaves of plants that had not yet had time to wither. It is as if the impact compressed fire, flood, and ash into a single, unbroken sequence. The precision of the record is staggering. Spherules can be dated to within hours of the impact, their chemistry matching Chicxulub ejecta perfectly. The layering of sediment shows events unfolding in sequence. First the rain of molten glass, then the river surges, then the settling of ash. Even delicate structures, like fish fins and insect wings, are preserved, undisturbed by scavengers or decay. It suggests burial so rapid that nature had no time to erase the evidence. Tanis is not the slow record of extinction. It is the fossilized scream of a planet. For paleontologists, the site is a revelation. For decades, the debate over dinosaur extinction has turned on whether the impact was sudden death or the final blow to a long decline. Tanis makes the case brutally clear. Sudden, global, and immediate. Fish dying as glass rained into their mouths. Mammals buried before they could flee. A landscape overwhelmed not in centuries, but in a single day. Yet the site also raises haunting questions. Did dinosaurs still roam the forests nearby when the river surged? Did herds of triceratops hear the shockwave ripple through the ground beneath their feet? Were tyrannosaurs still hunting as the sky filled with fire? The evidence at Tanis says yes, because the fossils are not the weathered remnants of a long-dead population, but the fresh casualties of catastrophe. Standing at the edge of this fossil bed, one can almost see it unfold. A river winding through a lush Cretaceous floodplain, alive with fish and reptiles, lined with ferns and cycads. Then, without warning, the ground shudders, the sky grows strange, and glittering stones begin to fall like deadly rain. The fish leap and thrash, waves crash upriver, trees topple into the flood. And then silence, as layers of silt close over the chaos, sealing it for eternity. Tanis does more than tell us how the dinosaurs died. It shows us what extinction looks like at the speed of an instant. It transforms the abstract idea of catastrophe into something visceral and undeniable. When we hold a fossil fish from this site, its gills clogged with glass from the sky, we are holding the very moment when one world ended and another began. The dinosaurs' reign did not fade into twilight. It ended in a day of fire, flood, and darkness. And Tanis is the place where that day is written down in stone. When the asteroid struck, the fire did not end with the sky. The question scientists still wrestle with is not whether flames spread across the Earth, but how far and how fiercely. Was it a planet consumed, every forest from pole to pole reduced to ash? Or were the fires patchier, devastating in some regions but sparing in others? The rocks and models offer evidence, and between them lies a story of fire from the sky, meeting fire on the ground, of soot rising to choke the atmosphere and alter the climate in ways that sealed the dinosaurs' fate. The models begin with energy. A bolide 6 miles wide slammed into shallow seas with the force of billions of nuclear weapons. The impact vaporized rock, ejected molten debris, and hurled it halfway to space. As it fell back through the atmosphere, this incandescent hailstone storm re-entered at speeds that heated the air itself, a global oven. The theory goes that the atmosphere grew hot enough to ignite forests simultaneously across continents, a flash fry of the biosphere. This is the origin of the global wildfire vision, a planet wrapped in flame before the sun set on impact day. But the sediments complicate the story. In some regions, particularly North America, there are thick layers of soot and charcoal at the KPG boundary, clear signs of widespread burning. Charred plant fragments litter the record, suggesting forests and plains did indeed ignite. Yet in other regions, Europe, parts of the southern hemisphere, the layers are thinner, the signal less clear. If every forest on Earth had burned at once, why do we not see universal layers of charcoal? Perhaps the truth is more nuanced. The re-entering debris likely created intense radiant heat, enough to set fires where vegetation was dry and dense. In wetter regions, or where landscapes were less flammable, ignition may have been sporadic. This would explain why some areas show overwhelming charcoal deposits, while others do not. Fires may have been near global in extent, but patchy in their intensity enough to fill the atmosphere with soot, but not to erase every tree from every land. Soot is the key. Whether the fires were global or regional, they produced enough black carbon to rise high into the stratosphere. Once there, soot particles acted like a planetary shade, absorbing sunlight and plunging the Earth into months or years of darkness. Unlike dust, which settles relatively quickly, soot lingers aloft, trapping heat above, but preventing it from reaching the surface. It was this feedback that made wildfires more than destruction on the ground. It made them a climate force, locking in the impact winter that followed. The consequences of that soot were devastating. Photosynthesis collapsed as sunlight dimmed, starving ecosystems at their foundation. Temperatures plummeted as heat from the sun was blocked, even while the upper atmosphere sweltered under the soot's absorption. Rainfall patterns shifted, oceans cooled, and food webs fractured. Charcoal in the rocks is not just the residue of trees burned, it is the residue of a planet's thermostat being yanked to extremes. Still, the imagery of a world consumed entirely by fire may not be accurate. Studies of fossil pollen and spores suggest that in some regions, pockets of vegetation survived the immediate aftermath. In New Zealand and parts of Antarctica, forests regrew surprisingly quickly, indicating they had not been completely annihilated. The extinction, then, was not about every tree burning, but about the systemic consequences of enough fires burning to alter the sky. It was not total incineration, but targeted devastation, amplified by atmospheric chemistry. For dinosaurs, the difference may not have mattered, whether every forest burned or only most. The effect was the same. Food chains collapsed. Herbivores could not find enough to eat. Predators starved in turn, and even the survivors faced toxic air. Soot inhaled would have blackened lungs and weakened bodies. The fires took life directly, but their smoke ensured that many who survived the flames perished in the dark years that followed. It is a haunting image. Forests ignited not by lightning or drought, but by a rain of molten glass from the heavens. Rivers clogged with burning debris. animals fleeing from walls of flame, skies choked with smoke that spread across continents. And yet, beneath the drama lies chemistry, the quiet fact that soot, once lifted into the stratosphere, can turn a planet cold. It is this detail that makes the debate about global versus regional fires more than academic. The scale of burning determined the scale of soot, and the scale of soot determined how long Earth lay under its shroud. The truth may be that both sides are correct in part. Some landscapes were annihilated in apocalyptic infernos, others only scorched, but together they produced enough smoke to darken the world. The fires themselves were horror enough, but it was their shadow in the sky that truly ended an age. When we look at the charcoal line in ancient rock, we are not just seeing burned wood. We are seeing feedback loops that turned fire into famine, flame into frost. The dinosaurs may have roared their last while flames consumed their forests, but it was the soot, the silent residue of that burning, that guaranteed the sun would not return in time to save them. Fire from the sky had become fire on the ground, and together they rewrote the future of life. In the fragile years after the asteroid strike, survival was not measured only in days of hunger or months of darkness, but in the rhythm of generations. For the great reptiles of the Cretaceous, their very mode of reproduction became a trap. Dinosaurs, for all their diversity, were still egg layers. Their future depended on fragile shells buried in earth or sand, warmed by sun, soil, or the parents themselves. In a stable climate, this strategy had served them for over 100 million years. But in a shattered world of firestorms, cold snaps, and erratic seasons, eggs became liabilities. It was the baby problem, an invisible curse that stalked the survivors long after the first shockwaves faded. Temperature was the first hurdle. Dinosaur eggs, like those of modern reptiles and birds, required narrow thermal windows to develop. Too cold, and the embryos stalled or died. Too hot, and the delicate balance of proteins unraveled. After the impact, the global thermostat lurched violently. Soot-darkened skies plunged temperatures downward, while sulfur aerosols created unpredictable swings between freezing nights and scorching days. A clutch buried in the soil might find itself in conditions hostile to life before the hatchlings ever stirred. Even species that guarded their nests could not shield them from climate chaos that shifted faster than instinct could adapt. The vulnerability of nests compounded the crisis. Wildfires swept landscapes with frightening regularity, destroying not just adult food sources, but the hidden caches of eggs. Floods, triggered by torrential post-impact rains, washed away carefully dug burrows and sand mounds. Predators and scavengers, desperate in the famine that followed, turned to eggs as easy targets. A triceratops might still manage to forage in the ruined forests. But if her clutch was drowned, burned, or eaten, her genetic line ended at the nest. Generational renewal slowed to a crawl. Just when the pressure for resilience was greatest, the scale of the problem widened with body size. Large dinosaurs, especially the colossal sauropods, faced longer incubation periods, months of waiting for a vulnerable clutch to hatch. That meant more time for disaster to strike. Mammals, in contrast, carried their young internally, sheltering them through gestation, and fed them with milk afterward. Even in famine, a mammalian infant could survive so long as its mother endured. Birds, too, had advantages. Many produced smaller eggs, shorter incubation times, and in some cases, the ability to re-nest quickly if a clutch was lost. The dinosaurs, bound to slower cycles, could not keep pace. Generational lag proved fatal. After the catastrophe, the survivors needed rapid recovery. Populations that could rebound quickly filled empty niches and stabilized food webs. But dinosaurs could not replace themselves fast enough. Each lost clutch set back recovery by a year or more. Each failed season pushed them closer to the edge. Mammals, with their faster cycles, began to spread into the void. Within a few thousand years, the imbalance between egg layers and live bearers was already reshaping ecosystems. Fossil evidence bears out this slow unraveling. In sediments above the impact layer, dinosaur eggshell fragments become rarer, while signs of bird nests persist. The diversity of egg types shrinks, suggesting that only a handful of clades managed to keep reproducing at all. Hatchling bones, once common in late Cretaceous deposits, nearly vanish from the early Paleogene record. It is as though the dinosaurs' nurseries had gone silent. The baby problem extended beyond simple numbers. Eggs tie a species to place. A mother must return to nest sites, invest time in guarding them, and depend on local stability. In a world of shifting climates and unstable ecosystems, that dependency became dangerous. Mammals could carry their young as they foraged or migrated. Birds could fly to new territories, build new nests, and spread risk across landscapes. Dinosaurs, however, were anchored to the ground, vulnerable to whatever calamity struck the nesting grounds. Their reproductive strategy, once a strength that allowed immense clutches and explosive hatching events, became a shackle dragging them into extinction. The tragedy is almost invisible in the fossil record. We see adult skeletons, imposing and complete, and we imagine their downfall as sudden and violent. But the deeper truth may be quieter. Nests that failed, clutches that never hatched, generations that never rose to replace their parents. The giants may have survived the first years of impact winter, but if their eggs did not, the species was already doomed. It is telling that the line of dinosaurs that survived the birds were the ones whose egg-laying strategies were flexible. Small clutches, short incubation times, rapid growth after hatching, and in many cases, parental care that buffered the young against harsh conditions. In them, the baby problem was minimized, enough to carry their lineage forward. For the rest, the catastrophe was not only about being colossal, slow, or specialized. It was about the fragility of the next generation in a world where the climate no longer kept promises. Extinction, then, was not just a single blow from the sky. It was a cascade of failures across seasons, years, and lifetimes. Eggs buried in ash that never warmed, nests drowned by storms, hatchlings starved before they could grow. The dinosaurs' age ended not only in fire, but in silence, in clutches that never cracked open, in babies that never saw the light of day. Their problem was not only survival in the present, but renewal for the future. And when that renewal faltered, their story reached its inevitable end. When you hold a piece of quartz in your hand, it feels timeless, clear, crystalline, stable, the kind of mineral that could outlast mountains. But under a microscope, that same quartz can tell a story of violence measured not in eons, but in nanoseconds. Within its lattice, scars remain from forces so immense, they rewrote the mineral's very structure. These are shocked grains, tiny fragments of the Earth's crust that still carry the trauma of the Chicxulub impact. They are the fingerprints of catastrophe, written in a medium that usually resists change. Quartz, in its normal state, has an orderly internal pattern. Atoms stack in a lattice that makes it hard, durable, and common in the sand of every beach. But when struck by pressures 1,000,000 times greater than the weight of the atmosphere, that lattice buckles, planes slip, bonds stretch, and the crystal reorganizes into forms it could never otherwise achieve. Under a polarizing microscope, those slip planes appear as tiny parallel lines shocked lamellae that reveal, unmistakably, an encounter with incomprehensible force. No volcanic eruption, no earthly tectonics can replicate the pattern. Only an impact, sudden and overwhelming, can leave such scars. At sites across the globe, these shocked grains are found precisely at the KPG boundary. In Italy, in Colorado, in Denmark, the same tiny structures whisper the same tale. Something struck the Earth with energy far beyond anything generated by plate tectonics. Even if we lacked the crater in the Yucatan, these grains would point to an impact. They are fragments of witness testimony, scattered across continents, all describing the same blow. Zircon tells a different part of the story. Unlike quartz, zircon is used by geologists as a timekeeper. Its internal clock set by uranium atoms that slowly decay into lead. Normally, zircons record millions of years with patient precision, each grain a diary of geological time. But when the Chicxulub asteroid struck, those clocks were jolted. Some zircons melted, resetting their timers. Others fractured, their crystalline order disrupted. By analyzing these changes, scientists can pinpoint the exact nanosecond scale shock that altered them. It is a rare moment where physics that unfolds faster than the blink of an eye intersects with dating methods that span entire eras. In drill cores from the buried crater, these minerals form a forensic archive. Shocked quartz marks the energy that blasted rock into the stratosphere. Melted zircons capture the pulse of heat that followed, as rock reached temperatures hotter than volcanoes. Together, they bridge scales. The instant of impact preserved in structures that geologists can date 66 million years later. Each grain is both a stopwatch and a scar. Proof that the catastrophe was not just a theory but an event, singular and global. What makes these findings so compelling is their ubiquity. You can travel thousands of kilometers from the crater, dig into the boundary clay, and still find shocked grains mixed among iridium and soot. The impact did not just scar one coastline. It sprayed trauma across the entire planet. Every shocked quartz grain is a piece of the Yucatan, shattered and flung outward to settle in rivers, lakes, and seas half a world away. The earth itself became a canvas, its sediments sprinkled with shards of broken crystal that all point back to a single, horrific second. The physics behind this is staggering. When the asteroid hit, pressure waves shot through rock at speeds exceeding several kilometers per second. For an instant, pressures reached hundreds of gigapascals, enough to mimic the conditions deep inside Earth's mantle. Rocks at the surface behaved like fluids, their atoms rearranged before they could even absorb the shock. It was violence compressed into less than the blink of an eye. Yet its traces are so indelible they remain readable after tens of millions of years. In that sense, shocked minerals are time travelers. They carry the immediacy of catastrophe into the deep time of geology, allowing us to stand in the present and glimpse the moment when the Mesozoic ended. They are the most reliable witnesses, incapable of exaggeration. Their testimony etched in atomic patterns. When geochemists peer into them with electron microscopes, they are not just studying crystals. They are listening to the echo of an explosion that shook the planet. And there is something strangely poetic in it. The dinosaurs left bones, the forests left charcoal, the oceans left silence in their sediments. But the rocks themselves, the most enduring part of Earth, also carry memory. Quartz fractured in an instant. Zircon clocks reset by fire. Minerals forever altered by forces beyond imagination. The impact left not only a crater, but a library of scars. A story written in shock that tells us with absolute clarity the world ended in violence, and the evidence is still under our feet. To touch a grain of shocked quartz is to bridge the gap between nanosecond physics and million-year timelines. It is to hold both the brevity of catastrophe and the endurance of memory in a single shard. Long after the dinosaurs vanished, long after the crater itself was buried beneath younger rocks, these crystals kept their secret, waiting for someone to notice. And when we did, they spoke. The end of an age had come in a single, incomprehensible heartbeat, and the stones themselves had never forgotten. The end of the Cretaceous was not just a story of one blow from the sky. Deep beneath the crust, another drama was already underway. One that had been unfolding for hundreds of thousands of years. The Deccan Traps eruptions in what is now India. These were not ordinary volcanoes. They were cataclysms of molten rock, pulses of lava that poured across the land in flows hundreds of feet thick, ultimately covering an area the size of modern Europe. Over the course of 1 million years, they released enough gas to rewire the planet's climate. But the question that haunts geologists is whether the asteroid's arrival did more than coincide with these eruptions. Did it accelerate them? Did it shake Earth's plumbing system so violently that it turned up the volume of an already simmering crisis? The chain reaction hypothesis suggests exactly that. When the Chicxulub asteroid slammed into shallow seas in the Yucatan, it sent shockwaves not just through the atmosphere and oceans, but through the solid Earth itself. Seismic energy rippled around the globe, magnitudes higher than the greatest earthquakes ever recorded by humans. The crust rang like a bell. In India, nearly on the other side of the planet, vast magma reservoirs lurked beneath the surface, feeding a volcanic system that had been erupting episodically. The sudden jolt may have fractured rock, opened new pathways, and unleashed a surge of eruptions that coincided with the extinction window. The evidence is compelling, if not yet conclusive. Recent high-precision dating of lava flows suggests a major intensification of activity right after the impact. Before the asteroid, the Deccan Traps were erupting, but more slowly, releasing steady pulses of gas and lava. Afterward, the volume and tempo appear to have increased, as though someone had opened the valves wider. The flows became thicker, more widespread, the gas output more catastrophic. It is as if the asteroid did not just kill with its own impact, but also amplified the Earth's ongoing fever. To visualize this, imagine Earth's mantle as a vast cauldron of molten rock, its surface crust riddled with cracks and weaknesses. Pressure builds slowly, magma rising toward the surface along pathways it carves over thousands of years. Now strike the planet with an asteroid 6 miles wide. The energy travels in seismic waves, compressing and expanding the crust, rattling faults and shaking magma chambers. For reservoirs already close to eruption, that stress might be enough to tip them over the edge. What might have taken centuries or millennia to unfold could instead erupt in decades. This hypothesis helps resolve one of the puzzles of the extinction: timing. If the Deccan Traps had erupted steadily for 1 million years, why did extinction line up so precisely with the asteroid? By tying the two together, the scenario explains both. The asteroid delivered the knockout blow, but in doing so, it may have jolted Earth into paroxysms that worsened the aftermath. The climate record fits this picture. Geochemical evidence shows pulses of carbon dioxide and sulfur dioxide in the years after impact, enough to alternate between hothouse warming and volcanic winters. Acid rain scoured landscapes. Mercury spiked in sediments, and oceans staggered under the combined assault of cooling soot from fires and warming greenhouse gases from lava flows. The result was climate chaos that stretched not just for months or years, but for tens of thousands of years, delaying recovery and finishing off ecosystems already staggering from the impact. Skeptics point out that the Deccan eruptions were vast enough on their own to influence climate, asteroid or not. They argue that the eruptions were already intensifying, and that the impact was coincidence rather than cause. The dating margins are still fine enough to leave room for debate. But even coincidence becomes synergy when two planetary catastrophes overlap. An asteroid impact and a continental flood basalt eruption happening in the same geological instant is no ordinary accident. Together, they delivered a 1-2 punch unlike anything Earth had seen in hundreds of millions of years. The imagery is stark. In the Yucatan, forests burn, oceans boil, skies darken with soot. In India, rivers of fire spill from fissures, blanketing the land in black rock while choking the atmosphere with sulfurous fumes. The dinosaurs did not face a single apocalypse but a duet of disasters, one from the heavens, one from the deep earth. And if the asteroid really did turn up the volcanic thermostat, then the end of the Cretaceous was not a singular tragedy, but a chain reaction in which every part of the planet conspired against its largest inhabitants. What is most remarkable is that the Earth itself may have been complicit. The asteroid did not just hit the surface and bounce off into history. It rattled the entire planet, setting off consequences thousands of miles away, releasing eruptions that buried half a continent under lava and doubled down on the climate chaos. The Deccan Traps and Chicxulub may have been two voices in the same symphony of extinction, one percussion, one bass, striking in sequence but harmonizing in destruction. In this view, the asteroid was not just the end, but also the trigger of Earth's own machinery, a cosmic bullet that also pulled the volcanic trigger. And that raises an unsettling possibility. Perhaps extinction was not inevitable from the impact alone. Perhaps, without the asteroid, dinosaurs might have endured the volcanic onslaught. Or perhaps, without the volcanoes, they might have weathered the impact winter. But together, their fates were sealed. When geologists chip into the black basalt cliffs of the Deccan Plateau today, they are looking at frozen rivers of a planet in convulsion, layer upon layer of hardened lava, stacked like pages in a book, record the story of Earth at its most volatile, and hidden between those pages is a question still unresolved. Were these eruptions Earth's independent voice, or were they the aftershock of a cosmic calamity? Either way, they remind us that extinction is rarely the work of a single hand. It is the result of converging forces, the planet itself echoing catastrophe, until life, as it had been known, could no longer stand. In the aftermath of the impact, the skies did not simply darken, they changed the rules of life itself. For the vast plant-eaters of the late Cretaceous creatures that had once thundered across floodplains and towered above forests, food was no longer just scarce. It was vanishing in ways that no size, no reach of neck, no grinding teeth could overcome. The story of the last herbivores is not merely one of hunger, but of plants failing under dim skies, their metabolism breaking down, their chemistry betraying the animals that depended on them. It was a collapse that began with photosynthesis and ended in extinction. Most plants of the Cretaceous relied on the sea-tree pathway, a method of capturing carbon dioxide that works well in stable, sunny conditions. These plants, ferns, cycads, conifers, flowering shrubs, and trees were the foundation of the great dinosaur ecosystems. But the asteroid and the Deccan Traps did more than scorch forests. They filled the air with soot, dust, and aerosols that blotted out the sun. Under these conditions, C3 plants faltered, their photosynthetic machinery, already inefficient under low light, became almost useless. Leaves starved before they could even unfurl. Growth slowed to a crawl, and entire forests withered before new seedlings could take hold. Sea-core plants, which thrive in hotter, drier, and brighter environments, had not yet spread widely. Grasses existed, but were minor players. More scattered ground cover than vast savanna. Their metabolic advantages would only emerge millions of years later. In the late Cretaceous, this meant that the herbivores had no resilient backup. When the C3 plants failed, so too did the food chains that towered above them. Fossil leaves record the stress. Many, preserved in boundary sediments, show damage from insects that gnawed desperately at shrinking foliage. Others display stunted growth, narrow veins, and malformed structures, signs of plants struggling under chemical and light stress. The damage was not only visible, but nutritional. Plants grown under high carbon dioxide or acid rain conditions change their chemistry. Their leaves become tougher, less digestible, filled with compounds that repel rather than nourish. For an animal the size of a hadrosaur, eating tons of greenery a week, the difference between nutritious foliage and chemically defended scraps meant the difference between life and death. Imagine a triceratops wandering through a dimmed forest. The cycads it once browsed are skeletal, their fronds chewed down to nubs. The ferns in the undergrowth are blackened by ash. A fallen conifer still carries needles, but they are brittle, their inner chemistry warped by weeks of low sunlight. The great animal lowers its beak, bites down, and gains almost no energy for the effort. Around it, other herbivores do the same, competing for scraps in landscapes that no longer replenish themselves. Hunger spreads, not because the dinosaurs forgot how to eat, but because the plants forgot how to grow. The problem worsened as ecosystems unraveled from the bottom up. Insects that pollinated plants died off in droves, breaking reproductive cycles. Seeds buried in ash could not germinate without light or stable temperatures. Acid rain, fed by sulfur aerosols from both the impact and volcanoes, stripped nutrients from soils and scarred young leaves with lesions. Even where patches of greenery survived, they were under siege from every angle. The herbivores had no escape. They were bound by scale. The giants needed immense quantities of food just to sustain their bulk, and that food had to be plants with enough energy density to justify the search. Smaller animals could nibble fungi, seeds, or carrion, but a 20-ton sauropod could not live off crumbs. The very strategy that had made them rulers of the Cretaceous, the ability to turn entire forests into fuel, betrayed them when the forests failed. Their stomachs, vast fermentation chambers that had once given them strength, became empty vaults echoing with hunger. Fossil sites tell of this slow starvation. The diversity of large herbivores plummets in the sediments leading up to the boundary, even before the final blow. Hadrosaurs, once abundant, dwindle. Ceratopsians, once a dominant force in North America, become rare. Sauropods had already retreated from most continents, surviving only in isolated regions. It is as though the ecosystem had been eroding beneath their feet long before the sky fell. The extinction of the herbivores was more than the loss of the giants. It was the keystone collapse. Predators depended on them, landscapes were shaped by them, and their constant feeding had structured the very distribution of plants. With them gone, entire ecological networks unraveled. Apex predators found themselves without prey. Scavengers turned to carrion that soon ran out. Forests, no longer grazed, regrew in strange new patterns when conditions improved, laying the groundwork for mammal-dominated ecosystems. And yet, not all plant-eaters perished. Birds, descendants of small theropods, adapted by eating seeds, insects, and whatever scraps remained. Small mammals foraged underground, gnawed roots, stored caches. Their flexible diets gave them resilience when specialized. Herbivores failed. Some amphibians and reptiles survived by retreating into refuges where conditions remained marginally stable. But the great plant eaters, tied to abundant green worlds, could not survive when the green world dimmed. The image of the last herbivores is haunting. Massive creatures wandering through ashen landscapes, their stomachs empty, their eyes searching for foliage that would never return. They were not defeated in battle, not hunted into oblivion, not felled by disease. They were starved by physics and chemistry, by the collapse of the planetary photosynthetic engine. Their tragedy was not only extinction, but futility creatures built to consume a world that no longer existed. In the end, it was not just the asteroid or the volcanoes that doomed them. It was the dim skies and the failed leaves, the chemical betrayals of plants under stress, the absence of photosynthetic energy to feed bodies too large for famine. The last herbivores carried the weight of deep time in their bones, the grandeur of an age when Earth's biomass pulsed through their enormous frames. But when the light went out, their hunger was the silence that marked the end of their reign. When the world cracked open at the end of the Cretaceous, survival was not a matter of strength or size or even ferocity. The tyrannosaurs and triceratopses, apex predators and armored giants, were undone by the very qualities that had once made them supreme. Survival hinged instead on traits that seemed ordinary, even unremarkable. Feathers that kept in warmth, fat that stored energy through famine, burrows that shielded from fire and frost, seeds that carried calories across years, an omnivory that turned scraps into sustenance. The survivor's toolkit was not glamorous. It was pragmatic, quiet, flexible, and it was enough to outlast the apocalypse. Take feathers. For over 100 million years, feathers had evolved from simple filaments into elaborate structures, first for insulation, then for display, and eventually for flight. At the end of the world, their original function keeping heat mattered most. As ash and soot choked the skies and global temperatures plummeted, feathers made small dinosaurs and early birds into warm-blooded furnaces. They could conserve energy better, forage longer in the cold, and keep hatchlings alive in nests that otherwise would have frozen. Their plumage, once the canvas of mating dances, became a survival blanket. Fat was another unassuming ally. In mammals, fat served as a portable reserve, calories stored under skin or around organs, ready to burn when food ran scarce. During the long, dim years after the impact, fat was the difference between starvation and endurance. Animals with the ability to put on weight in times of abundance and burn it in famine had a buffer against extinction. Even small reserves could carry a shrew-sized mammal through weeks of scarcity. Dinosaurs, locked into enormous bulk and dependent on constant intake, lacked that reserve. Fat, though humble, was a survival currency. Burrows offered refuge when the world above turned hostile. Many small mammals, reptiles, and amphibians spent much of their lives underground, tunneling into soil, hiding in root systems, or occupying the burrows of others. When firestorms swept across the land, when the first acid rains fell, when the cold nights after the impact turned lethal, burrows muted the extremes. Temperature stayed more stable below ground. Food caches could be hidden. Predators were kept at bay. The Earth itself provided a bunker, not against nuclear warheads, but against planetary catastrophe. Those who lived in the dirt lived to see the dawn of a new age. Seeds were another miracle. Unlike delicate leaves or soft fruits, seeds are packages of energy designed to last. Many can remain dormant for years, waiting for the right conditions to sprout. Birds and mammals that could eat seeds found themselves with portable rations at the very moment the green world collapsed. A single seed contains dense calories that can be cracked, stored, or swallowed whole. Fossil evidence shows that seed-eating birds were among the few avian lineages to persist across the boundary, while others vanished. Seeds became survival capsules, bridging the gap until photosynthesis restarted. Omnivory may have been the most decisive trait of all. When ecosystems collapsed, specialists suffered. Animals adapted to narrow diets, giant plant eaters, apex carnivores. Fish that needed particular plankton could not adapt when their food vanished. Omnivores, by contrast, ate whatever they could find: insects, carrion, roots, seeds, fungi. Even each other. Small mammals scurried from carcass to shrub, gnawing bone one day and chewing tubers the next. Birds switched from insects to seeds to scavenging. Crocodiles dined on anything that washed into their rivers. This flexibility allowed populations to ride the waves of scarcity, always finding enough to keep going until the environment stabilized. Size itself became a tool. In a world with less sunlight, less food, and less stability, being small was an advantage. Small bodies required fewer calories, reproduced more quickly, and could exploit microhabitats inaccessible to giants. A shrew could live off insects in a rotting log, while a hadrosaur starved in an empty plain. The future belonged to the small, the adaptable, the quick breeding, not the monumental. The age of giants had ended, but the age of resilience had only begun. Even physiology played a role. Animals with flexible metabolisms, able to enter torpor or hibernation-like states, had an edge. Amphibians that could burrow into mud and wait out bad seasons. Reptiles that could slow their hearts and reduce their needs. Mammals that could shelter and sleep through lean periods. These strategies worked because they bought time. Extinction is often a race against time, and those who could stretch their endurance survived. What emerges from this picture is not a single silver bullet, but a toolkit, a bundle of traits that, together, tipped the odds. Feathers, fat, burrows, seeds, omnivory, small size, metabolic flexibility, each alone might not have been enough, but layered together, they created a web of resilience. They formed a survival package that could withstand sudden darkness, poisoned rain, wild temperature swings, and collapsed food webs. It is tempting to imagine the survivors as lucky, spared by chance. But luck is not random in evolution. It is shaped by traits tested in quieter times that suddenly become decisive in crisis. The mammals had been small for tens of millions of years, not because they foresaw an asteroid, but because that was the niche left to them. Their burrowing, their fat reserves, their flexibility, all were byproducts of living in the shadows of dinosaurs. When catastrophe came, those byproducts became lifelines. The survivor's toolkit did not just preserve life through disaster, it also shaped the future. Mammals, with their fat and fur, diversified into forms that would dominate the Cenozoic. Birds, with their feathers and seed-eating habits, spread across the skies. Crocodiles, with their sit-and-wait strategies, endured almost unchanged. Each carried forward not only genes but survival strategies forged in apocalypse. The dinosaurs' reign ended not because life lost its will, but because only some lives were prepared for chaos. The survivors were not the strongest, nor the most fearsome, but the most flexible. They endured because they carried the right tools in their bodies, their behaviours, their ecologies. When the smoke cleared and the sun slowly returned, it was those humble tools that allowed them to rise into a world that giants had abandoned. The lesson is stark. Survival is not always about dominance in the moment. It is about resilience when the world changes. At the boundary between Cretaceous and Paleogene, survival belonged to those with feathers to warm them, fat to feed them, burrows to hide them, seeds to nourish them, and appetites wide enough to embrace whatever remained. Out of that toolkit, the future was built. Extinction is often imagined as a single blow, the asteroid streaking through the atmosphere like a cosmic bullet. But the closer scientists look, the clearer it becomes that the end of the Cretaceous was not the work of one trigger, but of several disasters converging in the same breath of geological time. The real reason dinosaurs vanished is not that an asteroid struck, or that volcanoes roared, or that seas retreated, but that all of these things happened together, synchronized in a way that made survival almost impossible. It was the timing, the trap of catastrophes stacked like dominoes, toppling one into the next. Start with the seas. Throughout the late Cretaceous, shallow inland oceans had been shrinking. These seas were nurseries for life, warm, sunlit waters that supported plankton blooms, coral reefs, and countless fish. Their retreat meant less habitat, fewer food webs, and less buffering of climate. When the seafloors drained, coastlines lengthened, weather grew harsher, and continental climates became more extreme. Entire ecosystems fragmented, leaving dinosaurs and their prey with less margin for error. The safety net of the inland seas was gone. Now add the volcanoes. In India, the Deccan traps were erupting with a fury that dwarfed anything humans have ever seen. Lava poured across the land in sheets hundreds of feet thick, belching carbon dioxide that warmed the atmosphere and sulfur dioxide that cooled it in violent swings. Each pulse of gas twisted the planetary thermostat. One decade hotter, the next colder, rains acidic, skies hazed with aerosols. Life accustomed to stability found itself lurching through environmental whiplash. Forests faltered, oceans acidified, and plants altered their chemistry under stress. The world was already unstable, its ecosystem strained by volatility. Then came the asteroid, 6 miles wide, striking the Yucatan at 20 kilometers per second, releasing energy equal to billions of nuclear bombs. On its own, such an impact might have driven many species to extinction, but on top of a planet already staggering from sea level fall and volcanic upheaval, it was unbearable. The skies filled with soot and dust, photosynthesis stalled, and the climate flipped into impact winter. What had been cycles of stress became permanent catastrophe. This is the timing trap. None of these forces were unprecedented in Earth's history. Volcanoes had erupted before. Seas had risen and fallen. Even asteroid impacts had scarred the surface, but rarely had they coincided so precisely, each magnifying the other, each striking a biosphere already weakened. Dinosaurs, already challenged by fragmented habitats and volatile climates, had little resilience left when darkness fell. It was not just one domino tipping, it was all of them collapsing at once. The fossil record bears out this grim choreography. In the last few 100,000 years of the Cretaceous, diversity was thinning. Some groups of dinosaurs were declining, particularly the giants that needed endless greenery to survive. Plant fossils show stress from fluctuating climates, leaves scarred by acid rain and altered chemistry. Marine sediments record plankton in retreat even before the impact. Life was fraying. The asteroid simply tore the fabric apart. The real reason dinosaurs did not survive was that they were caught in this perfect storm. Had the asteroid come 10 million years earlier, in an age of higher seas and more stable climate, perhaps ecosystems would have rebounded. Had the volcanoes erupted in isolation, perhaps animals would have adapted over centuries. Had the seas drained more slowly, perhaps food webs could have shifted. But together, in the narrow window of the late Maastrichtian, the catastrophes stacked into a chain reaction that overwhelmed every system. Think of it as a symphony of disaster. The deep bass of tectonic drift lowering seas, the percussion of volcanoes pounding the air with sulfur and carbon, the strings of ecosystems straining against instability, and finally, the crashing cymbal of an asteroid strike. Alone, each sound might not have ended the performance. Together, they silenced the orchestra of the dinosaurs forever. This view also explains why some creatures survived. Small mammals, birds, crocodiles, turtle species that had the flexibility to endure chaos were not invincible, but resilient. They could slip through the cracks of catastrophe because their needs were smaller, their strategies broader. The dinosaurs, magnificent but inflexible, were caught in the timing trap. It was not fate, nor inevitability, nor the single act of a rock from space. It was the cruel precision of bad timing. Volcanoes peaking when seas collapsed, ecosystems wobbling, just as an asteroid tore open the sky. The world ended not from one cause, but from the coincidence of many, stacked so tightly that no escape was possible. This is the real reason the age of dinosaurs closed in fire, darkness, and silence. Their extinction was not a singular tragedy, but a convergence, the dominoes falling in sequence until the last giant fell. The silence after the impact was more than a pause in sound. It was a stilling of processes that had run for millions of years. Forests that once pulsed with insect hum stood in ruin, their trunks blackened, their leaves gone. Oceans that once shimmered with plankton turned empty and sour, stripped of their carbonate breath. Across the continents, the giants lay absent. For years, that felt like forever. The planet drifted through an aftermath of cold, darkness, and acid. Yet even here, in the void left by catastrophe, life held on, and in holding on it, set the stage for something astonishing. The first phase was winter without snow. Dust and soot injected into the stratosphere scattered sunlight away, dimming the globe to twilight. Average temperatures plunged, plants withered, and the food webs that had depended on steady photosynthesis collapsed. This was the long night, a span of years when nothing could truly thrive, only endure. Survivors shrank into refuges. Mammals burrowed, birds scavenged, crocodiles lingered in sluggish rivers. The earth was not dead, but it was deeply quiet. Its rhythms slowed to survival's minimum. In the oceans, the crisis cut even deeper. The rain of sulfur from both asteroid impact and volcanism turned waters acidic, stripping carbonates from shells and leaving plankton exposed. For generations, the base of the marine food web was broken. Coral reefs vanished. Calcifiers dwindled, and whole lineages of fish, mollusks, and marine reptiles disappeared. What survived were the hardy form's tiny plankton that could endure chemical stress, opportunistic species that could feed on detritus, and creatures able to exploit niches abandoned by the vanished. For decades, perhaps centuries, the seas were shadows of themselves. Yet catastrophe is not permanent. Dust and soot do not linger forever. Slowly, particle by particle, the atmosphere cleared. The sun returned, first as a pale light, then with strength enough to wake forests from their graveyards. Seeds that had lain dormant sprouted, mosses and ferns spread over the blackened soil, followed by hardy flowering plants. Fungal blooms that had feasted on death receded as living greenery reclaimed space. Insects, quick to reproduce, multiplied in step, and the small, waiting animals emerged to claim the world newly remade. The rebound carried a paradox. While the early years were defined by cold and famine, the later centuries swung toward heat. Carbon dioxide from the Deccan eruptions, coupled with greenhouse gases released from fires and the vaporized carbonate rocks of the Yucatan, accumulated in the atmosphere. Once the dust cleared, sunlight poured down into a planet wrapped in a thermal blanket. Global temperatures climbed, oceans warmed, and ice receded. After the long night, came a fever that lasted for tens of thousands of years. This climate instability created an evolutionary bottleneck that was also a crucible. With most large species gone, the survivors found themselves in open ecological space. Mammals, once tiny and nocturnal, exploded in diversity. They radiated into forms that filled the niches dinosaurs had vacated. Herbivores, predators, climbers, burrowers, swimmers, birds followed suit, their beaks and bodies experimenting with shapes for every diet and habitat. Crocodiles persisted as they had, unchanged guardians of rivers and swamps, reminders of the deep past. The fossil record reveals this burst. Within a few million years of the impact, mammalian lineages had spread across the continents, their brain sizes increasing, their bodies adapting to new diets. By 10 million years later, primates appeared in tropical forests, hoofed grazers spread across plains, and carnivores hunted in packs. The evolutionary bottleneck had compressed life into narrow margins, but as soon as conditions allowed, the survivors exploded outward, a burst of creativity written in DNA. Plants, too, took advantage of the clearing. Flowering plants, which had been diversifying in the Cretaceous but still shared space with cycads and conifers, surged ahead in the Paleogene. Forests grew dense with broadleaf trees, and grasslands began their long preparation for dominance. Pollinators co-evolved with blooms, painting the air with new networks of interdependence. From the ashes of extinction, ecosystems more complex than before emerged. What stands out about this aftermath is not only the loss, but the speed of renewal. Geologically speaking, recovery was astonishingly fast. Within a few centuries, forests regrew. Within 1 million years, ecosystems stabilized. Within 10 million, the planet supported an entirely new caste of dominant animals. The long night ended not in silence, but in a dawn brighter than expected. The pulse of evolution, quickened by the narrowing of life's funnel. For dinosaurs, the story closed. Only birds carried their lineage forward. Feathers now tuned to the new world's climates. Bodies reshaped for the niches of small predators, scavengers, and seed-eaters. The age of reptiles gave way to the age of mammals and birds. Not because they were stronger in any one sense, but because catastrophe had stripped the stage clean, forcing adaptation and rewarding flexibility. The end of the Cretaceous, then, was both apocalypse and genesis. It destroyed a world of giants and created a world of opportunity. The long night was the price, paid in silence, starvation, and decay. But when the skies cleared, when the CO2 warmed the planet, and plants once again stretched toward the sun, evolution answered with exuberance. From the narrowest bottleneck burst the diversity that still surrounds us today. The story of the aftermath is not only about what died, but what began. The end of the Cretaceous was not the end of life, it was the hinge of history, the dark interlude between two acts. Out of ruin came resilience, and from resilience, renewal. The dinosaurs' absence was the mammals' opening. The long night ended, and in its wake, a new age of life began. The story of the dinosaurs' extinction is not only a tale of vanished giants. It is a mirror held up to our own moment, a reminder that Earth has tipping points, that ecosystems can endure stress for centuries and then collapse in the span of years. When paleontologists and geologists trace the scars of the Cretaceous-Paleogene boundary, they are not simply piecing together a mystery of deep time. They are deciphering a warning that bad timing, stacked crises, and fragile systems can undo the strongest dominions. The echoes ring loudly in today's world. We live, like the dinosaurs did, in an age of plenty. Forests still rise, oceans still teem, Cities hum with power and motion, but beneath that surface lies stress. The climate, once stable, now swings with extremes of heat, drought, and storm. Carbon dioxide concentrations rise at rates faster than almost any moment in Earth's history, rivaling the volcanic outpourings of the Deccan Traps. Species vanish not one by one, but in accelerating chains. Coral reefs bleach, insect populations crash, and rainforests flicker between resilience and collapse. The stage is disturbingly familiar. What the end of the dinosaurs teaches is not simply that catastrophe comes, but how it comes. Rarely from one blow, more often from several shocks landing together, each magnifying the other. The asteroid would have been devastating, but paired with falling seas and roaring volcanoes, it became final. Today, we see similar stacking. Climate warming joins habitat loss, pollution joins overfishing, pandemics intersect with global trade, political crises entwine with resource scarcity. Alone, each challenge might be manageable. Together, they create a timing trap of our own. There is also the lesson of fragility hidden in abundance. Dinosaurs looked invincible. Apex predators roamed every continent. Herbivores filled every niche, their diversity astonishing. But that diversity masked vulnerability. Giant bodies required steady food supplies. Specialized niches offered little flexibility. Once ecosystems wavered, the largest and most specialized toppled first. We, too, live in a world of specialization. Our cities rely on global supply chains, our crops on narrow genetic bases, our economies on constant growth. What seems powerful may in fact be brittle. And then there is the silence of feedback loops. After the impact, the smoke rose and blotted out the sun, cooling the planet. But that cooling sparked other changes. Plants died, which killed herbivores, which collapsed predator populations. The chain reaction moved fast, feeding itself until entire ecosystems fell silent. Today, the parallels are visible in melting permafrost, releasing methane, warming seas, reducing plankton that absorb carbon, forest dieback, reducing rainfall and sparking more fires. Like the dinosaurs, we may be standing on the edge of cascades we cannot fully see until they are already running. Yet the story is not only warning, it is also resilience. Life did not end with the asteroid. It shrank, it suffered, it hid, but it endured. From burrows and seeds and feathers came the ancestors of today's birds, mammals, and ultimately ourselves. The survivor's toolkit flexibility, smallness, adaptability is a reminder that resilience comes not from brute force, but from agility. Our challenge is different, but the principle remains. Survival belongs to those who can bend without breaking, who can change when the world demands it. There is also hope in the speed of recovery. The long night lasted years, the recovery millions. But in geologic terms, that was quick. Life bursts forth when given space, opportunity, and time. For us, the question is whether recovery must come after collapse, or whether we can bend the arc before it snaps. Unlike dinosaurs, we know what is happening. We have instruments that measure carbon in the air, satellites that track forests, models that project futures. We can see the dominoes wobbling. Awareness gives us a chance to slow them, to catch them before they fall together. The echoes of the Cretaceous remind us that no rain is permanent, no abundance guaranteed. The dinosaurs had ruled for more than 150 million years, longer than our species has existed by 100-fold. Yet when bad timing arrived, their age ended abruptly. Our time has been brief, but our impact vast. The same Earth systems that sustained them sustain us, and they can turn against us if pushed too far. The asteroid is not coming for us, but we are building our own impacts. One emission, one cut forest, one overheated ocean at a time. What the dinosaurs' extinction teaches is humility. We are not immune to timing traps, to cascades of change that move faster than our ability to respond. But it also teaches urgency. Unlike them, we can see the pattern. We can model outcomes. We can imagine futures. Their bad timing is our advance warning. The question is whether we treat it as prophecy or as a call to act. The long night that followed the asteroid ended with new beginnings. Mammals, birds, flowering plants surging into empty niches. But the price was the loss of nearly 3/4 of species on Earth. If we allow our timing trap to close, the survivors will again inherit a quieter, emptier planet. The difference is that this time, we will have chosen it. Echoes, then, are not whispers from a dead past. They are alarms from a living Earth. The dinosaurs remind us that abundance is no shield, dominance no guarantee, and timing no friend when crises converge. Their end is not only history, it is rehearsal. The question left to us is whether we will listen, or whether we will let the dominoes fall again. The thunder has faded. Once, it shook the earth beneath the weight of titans, the crash of tails, the bellow of predators echoing across forests and floodplains. Now, the ground lies quiet. Where herds of horned giants once churned the soil, ferns reclaim the land. Where tyrants once stalked in shadows, only wind bends the grasses. The age of dinosaurs, magnificent and terrible, has ended. What remains are bones, fragments of power, frozen echoes of motion. Fossils lie scattered in rock like punctuation marks at the end of a long story. Each bone tells of vitality that no longer roams. The teeth of tyrannosaurs still bite, but only in stone. The crests of hadrosaurs still rise, but in silence. The armour of ankylosaurs gleams no more under Cretaceous suns. Entire worlds are collapsed into strata a few centimetres thick, a thin line of clay that marks a boundary sharper than any sword. Beneath it, abundance, complexity, and thunder. Above it, absence. It is as if the world turned a page and left a chapter unfinished. Yet endings are also beginnings. In the shadow of that boundary, something stirs. Tiny mammals scurry through undergrowth, gnawing seeds and insects. They had always been there, unseen under the feet of giants. But now, the canopy above is open. They no longer live in fear of talons that never close, jaws that no longer hunt. For them, the silence of thunder is not a loss, but an opportunity. It is the first breath of an age that will one day belong to them. In the trees, survivors with feathers lift their heads. Birds, the last dinosaurs, carry forward fragments of what once was. Their bones are hollow, their bodies small, but they bear the inheritance of scale and wing. In their songs, faint and fragile, is the echo of the Mesozoic. They are living embers from the fire that went out, keeping the flame alive in plumage and flight. The thunder of footsteps is gone, but in branches above the new mammals' heads, a different sound arises. Birdsong. It is a paradox, this ending. To walk through the fossil beds is to feel both awe and grief. Awe at the sheer scale of what life achieved, creatures so vast they remade ecosystems. Predators so fierce they shaped evolution itself, an empire of diversity that lasted over 150 million years. Grief at how suddenly it was lost, how easily abundance can be undone by coincidence, by timing, by forces beyond any creature's control. A meteor, a volcano, a shifting sea, and the world remade itself. And yet, from that remaking, we emerge. Without the end of dinosaurs, there is no flowering of mammals, no primates in forests, no humans walking with tools and memory. Their extinction is the prelude to our existence. Every fossil we dig is both a monument and a debt. We live because they fell. Their lost thunder is the silence upon which we built our song. The epilogue is not despair. It is continuity in another form. When the last great reptile fell, the earth did not stop. Life bent, shattered, and rebuilt. What dinosaurs carried for millions of years, motion, energy, adaptation, passed into other vessels, into fur and feather, into brain and claw, into hands that would one day carve their bones from stone and ask why. The age of mammals is not a replacement but a continuation, the next verse in a poem too long to sing in one voice. Picture the scene at the boundary. The air still reeks of smoke. Ash clings to leaves. In a clearing, a small bird perches on a charred branch. Around it, silence stretches a silence heavy with absence. Yet the bird opens its beak. A song spills into the air, delicate, defiant. It is not thunder. It is not power. It is persistence. That fragile thread of sound carries across the wasteland into the ears of creatures that will inherit the earth. It is the voice of survival. It is the voice of the last dinosaurs, refusing to vanish without leaving behind a trace of melody. The age of dinosaurs ended in fire and darkness. The age of mammals began in silence and song, and over that razor-thin line in the rocks, the bird sings still. An unbroken note bridging extinction and renewal. The thunder is gone, but its memory lingers in bones beneath our feet, in birds above our heads, and in the knowledge that every age ends and every ending begins again.